Hi, Frank Kane here, and I'll be your guide through the processing domain of the AWS Certified Big Data Specialty exam. There's a lot to cover in this section. We'll start with AWS Lambda, which plays an important role in connecting the various services that move your big data around. We'll then cover AWS Glue and explore how it can impart structure to your unstructured data in an S3 data lake and enable you to query that data in place in S3. We're then going to spend a lot of time on Elastic MapReduce. This is really at the heart of big data processing on AWS. It's a managed Hadoop cluster that allows you to run a wide variety of tools for processing massive data sets. In addition to Hadoop itself, you can run Apache Spark, Notebooks, Hive, HBase, Presto, Hue, Splunk, Flume, and much more. And you'll learn how all these technologies are used on EMR and the sorts of problems they are meant to solve. From there, we'll dive into the realm of machine learning and deep learning, and Amazon's machine learning service and SageMaker. Finally, we'll touch on the AWS data pipeline and how you can use it to chain together larger processing workflows. Included in this section are several quizzes and hands-on activities. You're going to build a product recommendation system using Apache Spark on an Elastic MapReduce cluster and predict order quantities using Amazon's ML service. So let's get started and learn how to process big data using AWS. Let's talk about AWS Lambda. Lambda is a serverless data processing tool that you can use. Let's talk about what that means. So what is Lambda? Basically, it's a way to run little snippets of code in the cloud. So if you have a little bit of code in pretty much any language you can imagine, Lambda can run that for you without you having to worry about what servers to run it on. So you don't have to go and provision a bunch of EC2 servers to run your code. Lambda does that for you. It thinks about the actual execution of your code. You just think about what the code itself does. So it is a serverless method of actually running little bits of code that will scale out continuously without you having to do anything. Lambda will automatically scale out the hardware that it's running on as needed, depending on how much data is coming into it. So you can see how this fits into a big data world. If you have a lot of data flowing in, Lambda will automatically scale itself up and down to handle the processing of that data dynamically. In the context of big data, it's often used to process data as it's moved around from one service to another. So some services don't talk directly to other services in AWS, but Lambda can be used as a glue between anything pretty much. So it can sit there and get triggered by some other service sending data into it, like a Kinesis data stream, reformat that information into a format required by some other service, send that data to another service for further processing, and maybe retrieve that data and send it back. So Lambda is just a way of running little stateless bits of code in the cloud that is often used to just glue different services together in big data. Let's look at an example. It's not always used for big data. A very common use of Lambda is in use of a serverless website. And it's actually possible to build a website without having any servers that you manage at all. This is called a serverless website, and you can do this with AWS Lambda. Now, you normally can't do this with a really dynamic website, but if you can build your website by just having static HTML and AJAX calls embedded within that HTML, well, you can serve that from S3 or something, right? And then the AJAX calls are all you need to deal with. So maybe you have an API gateway in Amazon that sort of serves as the wall between the outside clients and you, the interior of your system there. So let's say, for example, you have a website where someone needs to log in. That login request might go through the API gateway, which in turn would then get sent off to AWS Lambda. Lambda would say, okay, the website wants this person to log in. It could turn around and craft a request to Amazon Cognito to say, do you authenticate this user or not? Amazon Cognito will come back and say, sure, here's your token. Lambda could then format that result and send it back to the website. So Lambda is sort of the glue there between the website API and Cognito on the back end. Similarly, let's say that we're building like a chat application on our front end there. Maybe we need to retrieve the chat history for that user ID once they've logged in. So again, the API gateway would receive that request. Lambda would be triggered by that API request and say, okay, I need to go get the chat history for this user ID. How do I craft that request at DynamoDB? It would then turn around, craft that request to DynamoDB for that chat history, talk to DynamoDB to get that, and then send it back through the API gateway back to the website. So here you see Lambda often fills a role as sort of the glue between different services. That's exactly how we're going to use it in our own application here. Very soon we're going to build this out. You'll recall that in our order history app, previously we used a Kinesis consumer application running on an EC2 host to sort of serve as the glue between Kinesis data streams and Amazon DynamoDB. Now, we don't want to have to manage EC2 servers for such a simple task as that. We can use Lambda instead. That's a much better choice. So we're going to build a Lambda function that actually sits between our data stream that's receiving server logs coming in and between DynamoDB, where we want to store that data longer term. Lambda's just going to sit there waiting for triggers of events from the data stream, and each trigger event will actually have a batch of events that it needs to go through and extract each individual record and then turn around and write that into DynamoDB. So again, Lambda is just the glue between the data stream and some other service, in this case DynamoDB. Later in the course, we'll build out a transaction rate alarm. Its only purpose is to notify us when something unusual is happening on our system. So in this case, we have a Kinesis data stream that's receiving events that says something weird's going on that requires someone's attention. Lambda is going to be triggered by those data stream events, and it will then turn around and craft an SNS request to actually send out a message to your cell phone notifying you that something requires your attention. So yet again, Lambda is the glue between two different services that don't talk directly to each other, but because Lambda is just code, it can do anything. It can transform that data in any way. It can talk to any service on the back end you can imagine. It can do whatever you want. So it's sort of the magic glue that enables you to put different components together in creative ways, and this is just one example of that. So what's the big deal about serverless processing of your code? Why not just run it on a server? Well, even though Lambda is still running on servers under the hood, they're not servers that you manage, and that's a big deal. So Amazon has people with pagers to keep those servers working and dealing with all the patches and monitoring and hardware failures and stuff, so you don't have to. You don't think about that at all when you're running AWS Lambda. All you think about is the code that you have running on it. And yes, even though individual servers can be cheap, scaling those servers out can get very expensive very fast. And if you scale out a fleet to run your function to manage your peak capacity, you're going to end up paying for a lot of processing time that you're not even using when you're off peak. With Lambda, you only pay for the processing time that you're actually consuming, so that can be huge from a cost-saving standpoint. And although it's not so big of a deal in the big data world, if you're dealing with something like a serverless website, it does make it easier to split up your development between front-end development and back-end development. So all the back-end work can happen in your Lambda functions, while your front-end developers worry about all the static stuff on the front-end client website. So there are several main uses of Lambda. One is real-time file processing, so as new data is coming into S3 or some other destination within AWS, Lambda can be triggered and actually process that file however you want to. And that can include doing some rudimentary ETL, that's extract, transform, and load. So Lambda is just code. You can do whatever you want in there, and that includes doing ETL on incoming data. You can also do real-time stream processing, as we discussed, just listening for new events coming in on a Kinesis stream or a Kinesis Firehose stream. You can also use Lambda as a cron replacement. And this is interesting. You can use time as a trigger for a Lambda function as well. So just like you can trigger events using cron on a Linux system, you can trigger off Lambda events on some fixed schedule as well. So if you need something to happen once a day or once an hour or once a minute or whatever schedule you want, you can actually set that up to call your Lambda function periodically. And that might come in handy for kicking off daily batch jobs of something or something like that. And also it can process arbitrary events from AWS services. And as we'll see, there's a very long list of AWS services that can generate triggers to Lambda. Pretty much any language you want to develop in is supported by Lambda, which is great. Node.js, Python, Java, C#, Go, PowerShell, Ruby. So you can process data and do whatever you want with it in pretty much whatever language you want. And this is huge because it means that any system that has an interface in any of these languages is fair game for your Lambda code. So remember, Lambda is code, and with code, anything is possible. So you don't have to just limit yourself to serving as a glue or a transformation between different AWS services. You could actually talk to other services outside of AWS if you want, or other libraries even that might enable you to perform more interesting transformations on that data. So really, you can use your imagination when you're using Lambda to do a lot of different stuff. It really makes a lot of things possible, all without managing servers in the process, which is awesome. Now, if you are using Lambda to serve as sort of the glue between AWS services, there's a long list of services here that actually trigger Lambda events for you. So any of these services can fire off triggers to Lambda functions whenever something interesting happens from these services. And this is just a partial list of them, guys. So also Alexa, and there's also manual invocation you can do of Lambda functions as well. Let's call out a few of the more common ones that are relevant to big data, though. And that would be S3, Kinesis, DynamoDB, SNS and SQS, and IoT. So you can integrate Lambda with S3. So whenever a predefined thing happens to an object within S3, that can act as an event data that will invoke a Lambda function. So for example, a new object is created in S3, you might have a Lambda trigger that picks up the creation of that object, turns around, parses out that information, and sticks it in Redshift or something. Same story with DynamoDB. And every time something is changed in a DynamoDB table, that can trigger event data that invokes a Lambda function as well. And that allows for real-time event-driven data processing for the data arriving in DynamoDB tables. You can integrate Lambda with Kinesis streams, and then the Lambda function can read records from a stream and be processed accordingly. Now, under the hood, Lambda is actually polling the Kinesis stream. The stream is not pushing data into Lambda. That can be an important distinction in some contexts there. So remember, when you have Kinesis streams talking to Lambda, Kinesis isn't actually pushing that data into Lambda, as the architectural diagrams might suggest. Lambda actually polls that stream periodically and collects information from it in a batch manner. You can also integrate Lambda with IoT, so when some device starts sending data to the IoT service, that can then invoke Lambda and process it accordingly as defined in your Lambda function. And it integrates with Kinesis Firehose. In that case, Lambda can transform the data and deliver that transformed data to S3 or Redshift or Elasticsearch or whatever you want. It can output to pretty much anything because you can write code to do what you want in response to these triggers. All AWS services have APIs you can call, so really the sky's the limit as to what you can call downstream from your Lambda function. You can do anything you want. These are just the ones that can trigger a Lambda function for you automatically. Now, as long as these services are all under the same account, you can set up IAM roles to allow Lambda to access them. So as long as all the services you're using are under that same account, pretty much Lambda can talk to them if you set up the proper IAM role. So one way you might use the Lambda service is integrating with Amazon's Elasticsearch service. We haven't talked a lot about Elasticsearch yet, but basically it's a real-time analytics system that we'll talk about more later. And you can use Lambda to automatically send data into it to be indexed. So the way this would work is you would have S3 receiving data somewhere, and you can set up a trigger so that as soon as new data is received into S3, it will notify AWS Lambda that there's new data to be processed. At that point, Lambda can turn around and process that data in some way and structure it in such a way that it can be imported into Amazon's Elasticsearch service and indexed into there for real-time analytics and things like that. A common use case of Elasticsearch is log processing. So if you have log data going into S3, Lambda could turn around and process that log as it's received, index it into Elasticsearch, and then you could use that to graphically query that data in near real time. It's kind of like a homegrown version of Google Analytics is one way to think about that. So Lambda serves as the glue there between S3, where the logs might live, and Elasticsearch service, where you're actually analyzing that log data. Another example of using Lambda would be with the data pipeline. So data pipeline, again, is AWS's method of chaining together a process for processing and importing and analyzing your data into a pipeline of data. So the idea here is that, again, you might want to do this on demand as new data is received. Now, normally with data pipeline, you schedule these pipelines so that you can set up a precondition that checks to see if new data is present in S3 before it kicks off, but it's still going to be running on a regular schedule normally. But by using Lambda, you can kick that off on demand. So if you have new data being received in S3 and you don't know when it's going to come in, it's not coming in on some regular schedule, using Lambda might make sense. The way this would work is, again, you'd have S3 send off a trigger to Lambda when new data is received. Lambda would then turn around and kick off that data pipeline once that data comes in. So in that way, you can process the data as soon as it's received instead of on some regular schedule that you've defined ahead of time. It can also be used with Redshift. And Redshift, again, is Amazon's data warehouse product and a big focus of the exam. Now, the best practice for loading data into Redshift is using the copy command. Basically a command to say, go copy data from here and put it in Redshift. But again, if you need to respond to new data that can show up at any time, you might want to use AWS Lambda to do that automatically when that new data comes in. So again, the idea would be that S3 would trigger Lambda whenever new data arrives, and then that can turn around and load that new data into Redshift. Now, the problem here is that Lambda is a stateless service. It can't keep track of where you left off by itself. So how does Lambda know where to pick up and where to leave off of when it's importing data from S3 into Redshift? Well, in order to do that, you need to use something like DynamoDB to store where you left off. So again, because AWS is stateless in and of itself, if you have persistent state that you need to maintain, such as where did I leave off on importing this data, you're going to have to tie into something like DynamoDB to keep track of that. So the idea here is DynamoDB would keep track of the files that have already been loaded, when it was loaded, and to which table. And that data would be used to batch up new files and copy them together using the copy command into Redshift. Lambda can also be used with Kinesis, and we've kind of seen this before. So let's say you have Kinesis streaming data going on. Now your Lambda code will receive an event with a batch of stream records, okay, coming in. And you can specify the batch size when you do that, up to 10,000 records. Now this seems straightforward enough. Streaming data comes into Lambda, you could pipe it out into Amazon Kinesis, and further processing happens. But there's a lot of little gotchas that can happen along the way. And a big focus of the exam, they love to throw these scenarios at you where something goes horribly wrong in your application and you have to figure out the best way to fix it. So these little details can be very important. So you need to realize that if your batch size for streaming data is too large, that could cause your Lambda service to time out. Now there is an upper limit on how long a Lambda function can run for. By default, it's 900 seconds maximum, but that could be configured to be even lower. So if your Lambda function takes too much time to process that batch of streaming data, it could fail, and that would cause a timeout, which will cause the whole system to back up. So that can be one source of errors. Now batches can also be split beyond Lambda's payload limit, so in addition to a timeout limit, there's also a payload limit of 6 megabytes. So you would have to take special steps to make sure that your batches are split if they do exceed 6 megabytes in data. That's another potential thing to look out for. Another thing to be aware of is that Lambda will automatically retry a batch of streaming data until it succeeds or until the data expires. That sounds like a great feature, but it can also cause problems. So if you're not handling errors properly, that could actually stall the entire shard, and that would be another failure mode that you need to be aware of. What happens if that's the case? Well, using more shards can help clear that case up. That way you can make sure that your processing isn't totally held up by errors when they're encountered. So if you do have a scenario where your batch keeps getting retried and an error keeps getting hit, and as it's stalling your entire pipeline, using more shards is probably one way of fixing that error. Also remember that Lambda processes shard data synchronously. It's not going to be splitting that data up and processing it in parallel. So you do need to take care about thinking about your batch size, how much data you're sending through in a single batch, and making sure that that's something that a synchronously processed Lambda function can get through within a short amount of time. The cost model of Lambda is really cheap. It's based just on the number of requests and how much memory your code consumes over time. Basically, you pay for what you use. And the free tier is really generous on Lambda. You get 1 million requests per month for free, as well as 400,000 gigabytes per second of compute time available. If you do need to go beyond that, it's only 20 cents per million requests, or 0.00001667 per gigabyte per second of throughput. So really cheap, and you'd have to be something really massive for that to add up to anything substantial. So that's great. You just pay for what you use with Lambda. There's no fixed baseline cost to it. Some other things that Lambda promises you are high availability. It does use replication and redundancy for that high availability. There is no scheduled downtime, and if your code fails, it will retry it up to 3 times automatically. They offer unlimited scalability, but that does come with an asterisk. There is a safety throttle in place of 1,000 concurrent executions per region. And again, you'd have to be doing something pretty massive to exceed that. So that's sort of their safety net for somebody having some bad code that's processing stuff way more than it should and running up a bill that's way more than it should be. If, however, you do have a legitimate need to exceed 1,000 concurrent executions per region, you can just ask AWS to lift that throttle for you, and they'll do it. Performance, they do offer high performance guarantees. New functions are callable within seconds after you publish them. Events can be processed within milliseconds, and it does that by caching your code automatically for you. Now, you do have to specify a timeout, so even though most things will be done in a matter of milliseconds, if you're doing processing synchronously of a large amount of data, you could design things in such a way that it doesn't work. That can cause problems. Now, the maximum timeout is 900 seconds or 15 minutes. So if you are doing some processing that takes more than 15 minutes for a given batch of data, that's going to cause problems and cause your system to fail. So Again, you do need to make sure that your processing is written in such a way that it can be completed relatively quickly, under 15 minutes in the worst case scenario. There are some anti-patterns for using Lambda that are defined in the AWS Big Data White Paper, so you should know about them. All of them come with caveats, though, so even though they say don't do this, there's always an exception of how you could do that if you wanted to. It's kind of a theme with AWS, it seems. So again, although you do have at most 900 seconds or 15 minutes to run your function, so for heavier processing where you really need to exceed that, you really should be using a system built on EC2 or something instead. But there is a workaround if you really, really want to use Lambda. You could chain multiple Lambda functions together. So if you can split up that processing into chunks that are less than 15 minutes apiece, you could, in theory, have a Lambda function that processes 10 minutes of the data, turns around and feeds the rest to another function that processes the next 10 minutes worth of data, et cetera, et cetera. I'm picking 10 minutes arbitrarily just because you want some safety margin there so that you're not hitting that 15-minute limit. Also, they say that Lambda is not a good choice for building dynamic websites. I kind of take issue with that because there's this whole world of serverless applications out there that depend on Lambda together with AJAX functions on the client side to construct websites that seem dynamic. But when they're talking about dynamic websites here, they're talking about systems that actually generate the entire HTML on the fly for an entire site. So you wouldn't want to be using Lambda to actually generate HTML for your website on demand. It's okay to use it for serving little snippets of it through serverless applications in AJAX. That's a perfectly good use of Lambda. But if you're going to be actually generating your website, the entire page dynamically, Lambda is probably not the best choice for that. For that, you want to be using something like EC2 and CloudFront for a truly dynamic website. Also, remember, you can't assume Lambda will run in any given environment, so you can't maintain information from one Lambda call to another. Lambda is, again, stateless. It cannot store information that passes from one Lambda call to another. They might be running together in parallel, remember, so that wouldn't make sense. But if you do need to store state information, you can still do that using DynamoDB or S3 to keep track of that state. So again, even though stateful applications is technically an anti-pattern for Lambda, you can do it if you work in something that can keep track of that state for you, such as DynamoDB or Amazon S3. So now that we know what AWS Lambda is all about, we can finally finish up our order history app requirement here. We're just going to fill in this last missing piece here. Already we've created our fake server logs on an EC2 instance. We've put those into a Kinesis data stream using the Kinesis agent. And we have a DynamoDB table set up to receive that data that an app could then talk to actually retrieve customer order information from an end user. The missing piece here is AWS Lambda. Right now we have a consumer script that's running on our EC2 instance playing this role, but obviously that's not a very scalable solution, just having a script running on one EC2 instance. It'd be much better if we had an AWS Lambda function running in a serverless environment on AWS that can scale itself up pretty much indefinitely on an as-needed basis. So let's go ahead and build out that Lambda function. Now note here that our Lambda function, in terms of security permissions, needs to consume data from a Kinesis stream, and it needs to write data into a DynamoDB. So with that in mind, let's start by creating IAM roles that our Lambda function can use to access the data that it needs and to write it out to DynamoDB. All right, so back to the AWS Management Console here. Let's go to IAM, Identity and Access Management. And we're going to go to Roles and create a role. The service that will use this role is Lambda. And now we can click on Next Permissions to specify the policies that we want to attach to this role. The ones we need are Amazon Kinesis read-only access. That's so we can read data from our stream, so check that off. And we also need to have access to DynamoDB. So for that, we're going to give it Amazon DynamoDB full access. Check that as well. Click the Next button. We don't need any tags, so we can then do a final review here. The role needs a name. Let's call it Cadabra Orders. And you can give it a better description if you want to. Double check that the two policies we want are there and hit Create Role. So now we have the IAM role that our Lambda function will need to talk to the services it needs to communicate with. All right, back to the AWS console. Now we're going to go to the Lambda service. So somewhere on your screen, there should be a big friendly create function button. If this is your first time to the Lambda dashboard, it might be somewhere else, but should be easy to find. We're going to author it from scratch. Let's give it a name. How about process orders? And for the runtime, we'll select Python 3 of some sort. Because if you know a language, odds are it's Python. We'll open up this change default execution role and say use an existing role and select the one that we just made, Cadabra orders. And there's more settings here under advanced, but we're not going to mess with them. If you want to be within a specific VPC, you can do that, code signing, but we're going to skip all that for now and just hit create function. So we have a shiny new Lambda function here called process orders. All we have to do now is wire it up. So what we want to do is add a trigger to actually feed data into this Lambda function from our Kinesis stream, Cadabra orders. So we need to wire up a trigger to monitor that Kinesis stream and feed data into our Lambda function as an input. And then we're going to write some Python code to actually turn around and store that data into DynamoDB. So to get started, let's hit add trigger. And we want a Kinesis trigger. And we will select our Cadabra orders stream. And the rest of the defaults here are pretty much okay. We don't want a consumer. The default batch size is fine. Default starting position is fine. So we're just going to hit add. And that appears to have worked. So now we need to give this thing some code to actually process that data that's coming in from Kinesis. And you can see that that Kinesis trigger has been wired into our Lambda function here now. So let's click on the process orders function itself and scroll down to the function code. Now it has some boilerplate code in here that you can look at and start from, but just to save you some typing, I've given you a copy of the complete Lambda function code within the course materials. So if you go to your course material download, you should go into the order history folder here. And from there, there is a lambda-function text file. Just open that up. Select all and copy it. And go ahead and paste it, replacing what's in there already. So if you look at this code, it's very similar to the consumer script that we ran on our EC2 instance earlier. It's just deserializing the data a little bit differently. So we have this extra code in here to decode the incoming stream that's being fed into Lambda. But once that's done, it's basically the same thing. So we just go through every line of data coming in, we parse it out, and then we just turn around and store it within DynamoDB using the batch_writer object that is part of the table DynamoDB object that comes out of Boto 3. So again, we're just using the Boto 3 library to simplify talking to DynamoDB here. Pretty simple what's going on here. Probably not a whole lot of point in going through this in too much detail. It's basically the same script that you looked at before, just with a little bit more wiring here to actually parse out the data from Lambda. All right, so let's hit save to store that. And at this point, we should be pretty much ready to go. So let's review here. Looks like everything has been successfully updated. We saved it. Our Kinesis trigger is in place, feeding data to the process orders script. And that script is actually handling storing that data into DynamoDB. So we don't have to explicitly add a destination for DynamoDB. The script itself is taking care of that for us. So with that, let's spark up our EC2 instance and play with it. Log in as EC2 user. And let's put some more log data in there. So sudo /log generator.py10. That should put another 10 instances into our DynamoDB instance if all goes well. So let's go to DynamoDB and look for it. Again, it will take a minute for that to get picked up, but let's go back to DynamoDB. Go to our tables, select Cadabra orders, and go to items. Looks like we have 10 in there so far, but after that Lambda function gets invoked, that should go up to 20 as soon as Kinesis Streams picks up those 10 new rows. So let's just sit here and refresh this until that changes to 20. And there we have it. We now have 20 items. So cool, it worked. That's awesome. So we've actually built this order history app out end to end, minus the actual app itself. There wouldn't be much value in building that out right now, but we have raw data going into an EC2 host, and that could be an entire fleet of EC2 hosts, right? We have a Kinesis agent sitting on each of those hosts that's pumping that data into a Kinesis stream, which in turn triggers a Lambda function that turns around and inserts that data into DynamoDB where our app can query it directly. If you want to poke around and see what's going on in more depth, there's also a metrics tab here where you can see what's going on with DynamoDB. And you can see there the metrics indicating that there is some activity going on here. We can also go back and look at Lambda in more detail if we wanted to. If you go to monitoring, we should see some activity here as well. And yeah, we have these single data points here reflecting our one little burst of activity there. So a way to monitor what's going on if you're running into trouble. You can also view the logs in CloudWatch if you want more data as to what's actually going on from your Lambda function if you need to debug things. But congratulations, we got this thing up and running. At this point, if you want to delete that Kinesis stream, you can. We are going to need it again later in the course when we're creating our order rate monitor, but if you are worried about money, it might be a good idea to delete that Kinesis stream and recreate it when we get back to that stage of the course. Again, that Kinesis stream does incur charges whether you're using it or not, as long as it exists, to the tune of about 30 cents per day. So keep that in mind. It will be easier to keep it up and running if you think you'll be working through this course relatively quickly. But if you're really sensitive about money, it'd be a good idea to go delete that Kinesis stream and just recreate it again when we need it later on. All right, let's move on. All right, let's talk about AWS Glue, which is a system for building your table definitions and performing ETL, extract, transform, and loading of your data automatically. Now, Glue is a huge deal on the exam right now. So back when they removed all of the machine learning content from the AWS Big Data exam, it was called at the time, into its own exam for machine learning, they kind of filled that gap mostly with more content about Glue and Redshift. So Glue really plays a major role in the exam today. So it's very important to pay attention to this section. There's not really a whole lot you need to know about Glue, but you need to really internalize it and understand how it connects all these different services together and how it might be used as pieces of larger applications. So what is Glue all about? Well, it's a serverless system. So again, there's nothing you need to maintain there that will automatically handle discovery and definition of table definitions and schema. So its main use is to serve as a central metadata repository for your data lake. It will discover those schemas out of your unstructured data sitting in S3 or whatever, and publish table definitions for use with analysis tools such as Athena or Redshift or EMR. So again, the purpose of Glue itself is to extract structure from your unstructured data. If you have data sitting in a data lake in S3, it can provide a schema for that so that you can query it using SQL or SQL-like tools, including RDS and Redshift and Athena and Amazon EMR and pretty much any other SQL database that can use a schema like that. The other thing Glue does is custom ETL jobs. So once it discovers that schema, it can do some processing of it for you. And this can be trigger-driven, based on when that data is received, or on a schedule, or on demand. And it's fully managed. So again, there's no services for you to maintain, no hardware for you to maintain. The ETL jobs use Apache Spark under the hood. We haven't talked about that yet, but Spark is a very popular system for distributed data processing. But you don't need to manage the Spark cluster, which is really nice. So you have the entire power of Apache Spark behind you with Glue ETL without having to manage that Spark cluster, which is a really, really nice thing. So one piece of it is the Glue crawler and data catalog, which it populates. So the purpose of the Amazon Glue crawler is to scan data in S3, and often it will infer that schema automatically just based on the data that it sees sitting there, but sometimes you have to give it some hints. You can schedule that to run periodically if you need to, and what that does is populate the Glue data catalog. So we have data sitting in S3, Glue can periodically or on demand scan that data and construct a schema of it. Again, that's just the table definition. What are the columns of data in that information that you have stored there in an unstructured manner? What's their data types? Things like that. Column names, it can infer that as well. Where it's stored, that's all important information as well. And it uses that information to allow things like Redshift, Athena, or systems running on EMR like Hive to query your unstructured data in S3 as if it were structured data, just like it were a traditional relational database. Now, the data itself remains where it was originally. So the data stays in S3. You're not duplicating that data. We're not copying it into an actual database table somewhere else. We're just using Glue to basically provide the glue between these relational database interfaces and the unstructured data lake that's sitting back here in S3. Once cataloged, that data is immediately available for analysis. And we'll build this out and go into a lot more detail into these systems later on. And then, once you actually have that data sitting in something like Athena, you can use something like Amazon QuickSight to visualize that data. So Glue, again, is the glue between your unstructured data and structured data analytics tools. So let's talk about Glue and S3 partitions really quickly here. So it's not entirely magic. You do need to think about how you're going to structure your unstructured data. I know that sounds backwards, but the way that you organize your data will affect how efficient Glue can work and how efficiently your systems can query this unstructured data. Now, the Glue crawler will extract partitions of your data based on how your S3 data is organized. So you want to think up front about how you're going to be querying your data lake in S3 and what those partitions should represent for the best performance. So for example, let's imagine that you have devices sending sensor data into your system, into your data lake every hour, just dumping raw data into S3. So think about, how are you going to use that data? Are you querying primarily by time ranges? If so, then you want to partition based on those time ranges, right? So you'd want to organize your S3 buckets as year, followed by month, followed by date, followed by device, okay? That way, we can start by winnowing things down by the year, and further by the month, furthermore by the date, and then finally by the device that generated that data. That will allow the partitions to really allow us to efficiently access data for a given date without having to slog through all the other information for other dates that we don't care about. On the other hand, if you're querying primarily by device and not by time, you might want to put the device up first. That way your primary partition would be the device ID and then followed by the year, month, and date. So if you're going to be querying for specific individual devices all the time, and that's kind of the primary thing you want to partition on, you'd want to make that the top level bucket that you're organizing your data under within S3. So this is something that you might see in the exam. What's the optimal way to organize your data that's being stored on S3 such that Glue can extract that and present it as partitions that make sense for what you're going to do with it? So we haven't talked about Apache Hive yet, but basically Hive is a service that you might be running on Elastic MapReduce that allows you to issue SQL-like queries on data that's accessible to your EMR cluster. I say SQL-like because technically it's called HiveQL, but the differences between HiveQL and SQL really aren't important for the purpose of the exam. What is important, though, is that you know that Glue can integrate with Hive. So you can use the AWS Glue data catalog that was extracted by your Glue crawler as your metadata store for Hive. And Hive, that's called a metastore. That's sort of special Hive terminology. Conversely, you can also import a Hive metastore into Glue. So if you have an existing Hive metastore or Hive database sitting in EMR, you can turn around and make a Glue data catalog out of that Hive metastore as well. You can go both ways. Now this will make a little bit more sense when we talk more about Hive in more depth later on, but just remember that the Glue data catalog can provide meta information to Hive running on EMR. So just like Glue can provide the glue between your unstructured data on S3 and Amazon services like Redshift and Athena, it can also provide the glue between services running on your EMR cluster, more traditional open source applications such as Apache Hive. Let's talk a little bit more depth about Glue ETL. Again, this is very important for the exam. Not a lot you need to know, but you need to know it. So make sure you internalize this stuff, folks. So Glue ETL will automatically or can automatically generate code for you for transforming your data. So you can go to the Amazon console and say how you want to transform your data in a graphical manner, and it will automatically generate code for you that will be running under Scala or Python and taking advantage of that Apache Spark engine that's running under the hood for Glue ETL. So you can also write your own code if you want to using Scala or Python. It will handle encryption, so you can have server-side encryption at rest or SSL encryption for handling data that's in transit. Those are both handled for you. Glue ETL can be event-driven, so you can have ETL processes that kick off automatically as soon as new data is seen by Glue. Also, something you might need to do is provisioning additional DPUs. That's a data processing unit to increase the performance of the underlying Spark jobs. So even though Glue bills itself as being fully managed, Under the hood, there are still servers that need to run these Spark jobs that are running the ETL processes for you. And if you find that it's taking too long, you can provision additional DPUs to give that Spark cluster that's running under the hood a little bit more capacity to work with. How do you know how many DPUs you need? Well, you can enable job metrics in your Glue ETL job to help understand the maximum capacity that you do need. So the process for figuring out how many DPUs you need to set for your cluster is to enable job metrics, study those, and then set the maximum capacity for DPUs in your job ahead of time. So that's the process you follow for tuning the performance of your Glue ETL job. If there are errors encountered along the Glue ETL pipeline, you can have those reported to CloudWatch automatically. And if you want to be notified of those, you could even tie CloudWatch into SNS to make sure that you get notified or get a text message or whatever it is if your ETL process runs into trouble. So again, I want to make sure you understand this. Glue ETL is a system that lets you automatically process and transform your data. You can do this by a graphical interface that lets you define how you want that transformation to work. And it will actually do that using Apache Spark under the hood, using Scala or Python code, fully encrypted both at rest and in transit. Can be event-driven if you want it to be, or can run on a schedule. A little bit more about Glue ETL. So again, just want to reinforce this. It can be used for transforming your data, cleaning your data, or enriching your data before doing analysis. It will generate that ETL code in Python or Scala, and you can actually modify that code if you need to once it's been generated. So if the generated code isn't doing exactly what you want, you can just go in and modify that code to tune it and do exactly what you want. So you can use the automatically generated code as sort of a starting point and build on top of that. That's a really great way to do more complicated operations using Glue ETL. You can also provide your own code if you want to hand it your own Spark or PySpark scripts. So a Spark script might be written in Scala, but if you prefer Python, which a lot of people in the data analytics world do, you can just provide a Python script for Spark called PySpark to Glue ETL to work with. And it will just hand that off to the underlying Apache Spark engine for transforming that data, cleaning it, enriching it, whatever you need to do to process that data before you actually analyze it using later systems. The target of Glue ETL can be S3, or it can be talking through a JDBC interface to some other database, including RDS or Redshift, or it can output data into the Glue data catalog. So you could have an ETL job that just generates a data catalog as well. Again, it is fully managed, although you do have some control over the underlying resources, how many DPUs you have, like we talked about. It's very cost effective. And again, with most of these serverless managed systems, you only pay for the resources that you can actually consume. The jobs are run on a serverless Spark platform. When we say serverless, yes, there are servers under the hood actually running that Spark code, but you don't see them. You don't have to manage them. So that's why we call it serverless. It's all kind of magic. There is a Glue scheduler you can use to schedule those jobs, or you can use Glue triggers to automatically run jobs based on whatever events you want. So please take a moment to internalize this slide and the information on it. Very important stuff to understand for the exam. So how do you go about applying these ETL transforms in Glue? Well, the main data structure that you'll be interacting with is called the dynamic frame. And if you're familiar with Apache Spark, this is going to feel very familiar. It's very much like a Spark data frame object. The only difference is that it has more ETL stuff available to you within that class. It has Scala and Python APIs available, whatever you prefer. And very much like a data frame is a collection of rows in Spark, a dynamic frame is a collection of dynamic records, where dynamic records are these self-describing records that have some sort of schema associated with them. So you can see in this diagram on the right here, you can think of the dynamic frame as encompassing a collection of dynamic records, and each dynamic record contains fields, columns, whatever you want to call them, within that record. In this case, ID, year, month, but could be anything, right? And you can have as many dynamic records as you want. Those will all be stored in a distributed manner, probably on S3 under the hood, right? So just to make it real, here's a few code snippets here. Remember that you'll never be asked to write code on the exam itself, but if you are a coder, this might help make it more concrete for you. For example, if we wanted to create a dynamic frame called pushdown events, we might just say glue context.getCatalogSource and load that from some database table somewhere. And then to apply a mapping to that dynamic frame, we could just call pushdownEvents.apply mapping. And what that will do is apply that mapping to every single record within that dynamic frame, of course, in a distributed manner. That's the whole point, right? So in this specific example, we're defining a mapping that converts the IDs from strings to longs. It's renaming the actor.login field to just actor, repo.name to just repo, so on and so forth. The details aren't terribly important, but it kind of drives home the concept here. You can create a dynamic frame, and in just a couple of lines of code here, we can apply some complex mapping to every single record in our dynamic frame in a distributed manner. Let's talk a little bit more about the transformations you can do with GlueETL. There are certain bundled transformations that come with it out of the box. That includes drop fields or drop null fields. So if you just want to remove empty data, which is a very common operation in pre-processing, it can do that for you with just a couple of clicks. So it can automatically drop fields or drop null fields to remove empty data from your incoming data for you. You can also do filters where you specify your own function for filtering records. So if you do need to specify some criteria where you want to throw out outliers or data that might not fall within the bounds that you expect, you can set up these filters to filter records out based on that criteria. Or maybe you just want to extract only a subset of your data to analyze. That's another valid use of filters, right? You might want to say, I only want to filter data from the US for this job, or I only want data from the UK, whatever it might be. A filter transformation will let you do that, and that is a bundled operation that's very easy to do with GlueETL. You can also do joins. That's also a bundled transformation that's provided as part of GlueETL. So if you need to enrich your data by joining it with other tables, you can do that. A common operation there is taking some code or like a country code or something and enriching that with the full name of that country. I don't want to get into database theory too much, but joins are generally used to enrich data. For example, I use the movie lens data set a lot in my courses, where you might have a movie ID. If you want to actually put the movie name into the output data, you might do a join with a separate table that maps movie IDs to movie names, as an example. You can also do maps, and this allows you to do things like add fields to your data, delete fields, or perform external lookups manually. So if you just need to transform your data one row at a time, maybe that just includes, selecting which fields that you want to pass on to the final analysis. That's a very common operation. You can use a map operation to do that. So for example, if there's a bunch of columns of data coming into your data, you can use a map operation in GlueETL to extract the fields that you actually care about and delete the ones that you don't care about. There are also bundled machine learning transformations. That's pretty cool stuff. One that you'll probably see mentioned on the exam is the find matches ML transformation. And its purpose in life is to identify duplicate or matching records in your data set, even if those records do not have a common unique identifier and no fields match exactly. So it can actually learn what a duplicate record looks like, even if it's not really a duplicate. For example, if you have duplicate addresses that vary, by some subtle thing, like somebody spelt out street instead of using the abbreviation, you might use find matches ML to handle that. So that's a tool that's available for you. Just remember, it exists, and that's what it does. You can also use GlueETL for format conversions, and some supported formats that it can automatically convert between are CSV, comma-separated values, JSON, Avro, Parquet, ORC, and XML. So a lot of times you'll have data coming in as one format and you need to transform it into something else for a downstream system. GlueETL can do that for you very easily. And also, since again it's using Apache Spark under the hood, anything Apache Spark can do, you can do with GlueETL. That includes even fancy things like k-means clustering. That's coming from Spark's MLlib package. We'll talk more about Spark later in the course, but just remember, anything Spark can do, you can do in ETL. So again, do take a moment to pay attention to this slide, guys. It is important to understand GlueETL in depth and what it can do. One more method on the Glue dynamic frame that I want to talk about is resolve choice. I'm hearing this is actually showing up on the exam now, so we should talk about it. Its purpose in life is to deal with ambiguities within your dynamic frame and return a new one that does not have ambiguities. What I mean by an ambiguity, well, for example, if I have two fields that have the same name within my data frame, that would be an ambiguity that we need to resolve somehow. And there are 4 ways right now that you can deal with those ambiguities. One is you could say make underscore calls as a parameter to the resolve choice API. And what that will do is create a new column for each unique type that name appears under. So look down here at the bottom. We have this example here where we have a my list dynamic frame that contains two fields called price. One of them is a numeric double precision number. The other one is a string that contains the $ symbol. So if we were to call make underscore calls on this example, we end up with two new columns, one called price underscore double and one called price underscore string to resolve that ambiguity. Another option is just cast, and that will force every instance to be cast to one specific type. We can also say make underscore struct, which creates a structure within your record where it contains each data type individually within that structure for price. So we might have a new structure there called price. Inside that price structure would be the decimal version and the string version of that field name. And finally, we have project, which will project every type to a given type. So for example, I could just say project : string, and that would force everything to be a string data type. So that would force the 100.00 decimal type to be a string instead. So that's what resolve choice is all about. It's just about resolving ambiguities where you have different columns with the same name within your dynamic frame. So sometimes the result of your ETL job is that you want to modify the data catalog itself as part of that. Maybe you've added some fields or tables or moved things around a little bit as a result. So how do you do that when you've had this crawler that ran that defined your schema? What happens when you want to change that schema later on after the fact? Well, there's a few ways of doing it. You might also need to change your partitioning as well as part of your ETL. You might choose to store that data differently under different partitions. Also something you need to deal with. Turns out there's a couple of ways. So you could just rerun the crawler again, but the other way would be to have your ETL script actually explicitly change the partitions by using the enable update catalog and partition keys options while it's setting things up. So that is possible to do. You can also update this table schema as well. Again, option A is to just rerun the crawler, but you could also do that from a script as well by using enable update catalog and update behavior to update the schema of a table explicitly once you're done processing it. You can also create new tables from your script. Again, you would use enable update catalog and update behavior for that, together with set catalog info to create new tables from your script if you need to. And there are some restrictions on doing all this stuff. First of all, modifying the data catalog from ETL can only be done when S3 is your underlying data store. It's also limited to JSON, CSV, Avro, and Parquet formats. And if you're using Parquet, there is some special code you need to know about when you're doing it. Also, nested schemas are not supported for this. So those are the gotchas with modifying your data catalog, but it is important to know that Glue ETL allows you to do this. You don't have to rerun the crawler in every case. Sometimes your script can actually add new partitions, update the table schema, or even create new tables right from the script. Another thing you need to know about with Glue is the existence of development endpoints. These allow you to develop your ETL scripts using a notebook environment where you're sort of interactively developing and iterating and testing your code within a web browser that's connected to one of these Glue development endpoint instances. Once you've developed that script using your notebook, you can then turn around and create an ETL job from it that runs your script using Apache Spark and Glue. Now the endpoint will be in a VPC that's controlled by security groups, so connecting to it from your browser can be a little bit tricky. One way of doing that would be using Apache Zeppelin on your local machine, which is a open source environment for running notebooks, or you could run a Zeppelin notebook server on EC2 using the Glue console. You could also use a SageMaker notebook to develop your ETL scripts using Glue development endpoints. So if you're using SageMaker to do some machine learning work, you can use the SageMaker notebook environment as well to integrate your ETL into part of that notebook too. You can also just use a terminal window that's connected to that endpoint instance. And again, as long as you're using SSH with the appropriate keys, just like you would with any other EC2 instance, that can work too. They also integrate with the professional edition of PyCharm. So if you're using that as your Python development environment, you can use that to automatically connect to a development endpoint for AWS Glue. And finally, you can use Elastic IPs to access a private endpoint address if you need to. So if you do have a development endpoint that's sitting there running all the time, you could use an Elastic IP to make sure you can get to that from the outside world. Running glue jobs, there's a few ways to do it. Again, one is to use a cron-style time-based schedule. So if you need to run that on some sort of a fixed schedule, you can do that. Same format as cron. Or you can have something called job bookmarks. Again, this is an important thing for the exam. So a job bookmark is used to persist state from the job run. So if you need to set things up so that you don't end up reprocessing the same data, a bookmark allows you to keep track of where you left off so that you can prevent the reprocessing of old data and just process that new data when you rerun on a schedule. So the job bookmark keeps track of where you left off when you're running your glue jobs on a schedule. It works with S3 sources in a variety of formats, and it can also work with relational databases via JDBC if your primary keys are in sequential order. Now that feature only handles new rows, not updated rows. So you can only use job bookmarks with a relational database if you are injecting new data as new rows. If it's going back and updating existing rows, job bookmarks won't work the way you expect. Might be an important thing to know. Also, CloudWatch events. So you can fire off a Lambda function or an SNS notification, whatever you want to do when an ETL job in Glue succeeds or fails. So Glue integrates with CloudWatch to keep track of what happened and to potentially notify you based on chained events through SNS or Lambda, whatever you want to do when that job succeeds or fails. Once that happens, you can invoke an EC2 run to do further processing, send the event on to Kinesis, activate a step function, whatever you might want to do. So just keep in mind, using CloudWatch, you can tie together Glue with other systems like EC2, Kinesis, or AWS step functions. Let's talk about Glue's cost model. It does a lot, and it's not free. Well, not usually. Basically, you're billed by the minute for your crawler and ETL jobs. So you're billed based on how much time your Glue crawlers take to extract those schemas from your data and how much time it takes for your ETL jobs to process and transform that data using Apache Spark. For storage, the first million objects stored and accessed are free for the Glue data catalog. So pretty generous allowance, but for big data applications, you might chew through a million objects relatively quickly. If you're using a development endpoint to actually edit your ETL scripts using a notebook, those will be charged by the minute. So make sure you shut those down when you're done. For every minute that you're using that notebook on a development endpoint for Glue, you will be billed for every one of those minutes. So the clock is running once you're doing that development. Don't just leave it running and go out to lunch for a week, right? Glue anti-patterns, what should you not use Glue for? Not much, really. They've put a lot of effort into making it as general purpose and flexible as possible. The one thing that they do tell you to avoid, though, is if you're trying to use multiple ETL engines. So again, remember Glue ETL is based on Apache Spark under the hood. If you really want to use other engines, such as Hive or Pig or something like that, you'd want to use Data Pipeline or maybe EMR to process that data instead. That would be a better fit. Although Apache Spark can do pretty much everything that you'd want to do these days. I can't really imagine an instance where you'd need to use Hive or Pig or something else instead of Spark, unless you have some legacy code or system that you need to integrate. What used to be an anti-pattern was streaming data with Glue ETL, but that's no longer true. As of April 2020, Glue ETL now supports serverless streaming ETL processes. So it can be hooked up to Kinesis or Kafka to ingest streaming data and transform that data and clean it in flight. That's pretty cool. It can then store the results into S3 or some other data store of your choice. How does it work? Well, it uses Apache's structured streaming under Apache Spark. So this is a not too new, but relatively new addition to Apache Spark, where structured streaming allows true real-time processing of streaming data. Under the hood, Apache Spark has these things called data sets that it uses to transform batches of data that it's working on. But with structured streaming, you basically have a data set that just keeps on growing forever as streaming data gets added to it. And it can transform that data using the same kind of code that you would use for batch processing. So if you have a Spark script on Glue ETL that's built for processing batch data, it's usually pretty easy to adapt that for streaming data as well, which is kind of a nice feature. We'll talk about Apache Spark in more depth later on, but streaming data is now A-OK with Glue ETL, so that's pretty cool. There are a few new features in AWS Glue. They seem to be investing a lot in this feature right now, so not sure you're going to see this on the exam quite yet, but you probably will soon. So one of these new features is called AWS Glue Studio, and basically it's a visual interface for defining and creating ETL workflows. So it allows you to create these more complex workflows where you might have multiple things happening in parallel from the same source, or maybe different sources being processed in parallel in different ways. But it lets you set up these complex jobs in a visual manner, and often without writing any code. So it offers you this visual job editor that I'll show you in a moment that allows you to create directed acyclic graphs for complex workflows like this. And the sources of that currently can include S3 or Kinesis or Kafka or any JDBC source as well. You can then graphically set up transforms of that data in the Glue Studio UI. So you can do transformations, you can sample the data, you can join tables together, and a few other things as well. And then you can take the output of that transform and send it to S3 or the Glue Data Catalog. It also supports partitioning out of the box. So if you do have partitioned data, it will automatically take advantage of that and accelerate itself accordingly. Also, it offers a visual job dashboard that lets you visualize the status of your Glue ETL jobs and how they're running, what's running, how long they've been taking. So that can be useful for quick troubleshooting and making sure that your jobs are running as expected. Let's dive in and show you how it actually works. So just to make Glue Studio real, again, the only really thing you need to know for the exam is what it is and what it's for. We're just going to give a quick tour of it here. You don't have to follow along. If you go to the Glue console here in AWS, you'll see there's an AWS Glue Studio link over here. Still has a new tag. I imagine that'll go away at some point, or Glue Studio might become the default view actually at some point. But for now, we have to click on that. And let's say we want to create a new job. We'll just click on Create or Manage Jobs. And you can see we can easily start here from a given source and target. So if my source data lives in S3, I can just select S3. Or it could be coming from RDS, Redshift, Kinesis, or Kafka as well. And then we need to stick the results of that somewhere, either S3 or into the Glue Data Catalog. So let's start with an S3 bucket and put it into another S3 bucket. Click Create. And you can see we have this graphical representation of a source for the data from S3, some sort of transformation we're going to apply to that, and the target for the resulting transform data. And you can see that we can build up these sort of connected acyclic. And we're not limited to these sequential steps of events here. We can set up more complicated trees here with a directed acyclic graph. And kind of like how Spark works under the hood, right? So that's no small coincidence. Glue ETL uses Spark itself, so it's not too surprising they've gone with a DAG structure here. So we can just click on the S3 bucket here and choose where that data is coming from. I'll just use an existing one that I have in place for the exercise for this part of the course. And then we can apply a transformation to it. We can just click on that existing one. Let's say we want to drop the description field and we want to make sure the year is an integer and the day is an integer. I'm just showing you how it works here. And we can click on the output schema to see what gets output from that transformation. You can see the year has been transformed to an integer, the day has been transformed to an integer, and that description field is gone now. And then from our S3 bucket here for the destination, we could specify where exactly that goes by browsing S3 and selecting a place for that to go. There's other stuff you can do too. Let's click back up here. And if you pull down the transform menu here, we can see there's a lot of different things you can do here graphically. We can apply mappings, drop fields, rename fields, join two tables together, split them. Let's do a filter. You can also do custom code here with a custom transformation if you still want to write code. But let's introduce a filter transformation. And we can just say add condition. And let's say we want to only get years that are before 2021 or something like that. And by adding that condition, we've actually added that filter to filter out anything earlier than 2021. We probably want to give that filter a destination as well. So let's give that a target going into S3 somewhere. And we probably don't need this intermediate target here, so we can remove that one. And we're back to this linear sequence of chained events here. But again, it doesn't have to be linear. You could split this off into multiple destinations and do all sorts of complicated processing in parallel, which is kind of the power of Glue Studio. You can have this sort of source data, split it up into multiple different transformations and put the outputs of those transformations into different places. So that's pretty cool. Now, something else you can do if you go back to the main Glue Studio page here is monitor job runs that you have running already. I don't have any running myself right now, but this gives you an idea of the sorts of things you could see here. It gives you the summary of how many jobs are running, how many have succeeded and failed, success rates, the resource usage, what types of jobs are running, the timeline, all sorts of information about your Glue ETL jobs in one graphical dashboard here for you. So that can make maintenance and seeing what's going on with your ETL jobs a lot easier, and troubleshooting stuff. So that is AWS Glue Studio in a nutshell. Another pretty new feature in AWS Glue is AWS Glue Data Brew. And this is a visual data preparation tool meant for graphically doing complex transformations on large data sets that might be coming from S3 or a data warehouse or a database of some sort, and putting the output into S3. You might say to yourself, that sounds an awful lot like Glue Studio, but it's a little more specific. It's more purpose-built. So Glue Studio lets you build up these complicated transforms on top of Glue for transforming data in complex workflows. But Glue Data Brew is really much more simple. It's just you take a data source and you build up these recipes, they call it, of transformations that you want to apply to that data source, and just put the output in some S3 bucket somewhere. So it doesn't have this directed acyclic graph of complicated workflows. It's just purpose-built for very quickly and very efficiently transforming a data set in some way. And you can transform it in a lot of different ways. There are over 250 ready-made transformations to choose from, including some pretty complicated stuff like imputing missing data and dealing with missing data, filtering things, whatever you can dream up. And we'll walk through that in more detail shortly. The basic idea is that you have a project that has some larger context of what you're trying to accomplish. Within that project, you can define jobs, and each job contains these recipes of transformations. That might be the sequence of multiple transformations that you apply to that given data set. You can output it to a variety of different formats into S3 with a variety of different compression types, pretty much anything you might want to use. Data is always getting new features. The latest in 2022 are the ability to define data quality rules as part of your transformations, and you can also now create new data sets using custom SQL from either Redshift or Snowflake. And security is always a concern. It does integrate with KMS. It is restricted to customer master keys only, though. For data in transit, it is secured with SSL. You can use an IAM policy and IAM roles to restrict who can do what with Data Brew and restrict what operations they can do, what data sets they can access, and things like that. And for auditing and troubleshooting, it does integrate with CloudWatch and CloudTrail. So let's dive into the console because it'll make a lot more sense when you see it. So let's just explore Glue Data Brew here a little bit. Again, I'll give you a little quick tour of the UI just to make it a little bit more intuitive as to what it's all about. So I'm at the Glue Data Brew console page here, and let's create a sample project, just using some of the sample data they provide. Let's explore popular baby names in 2020, and we'll create a new project in Data Brew for that. We need to give it a IAM role for security purposes. Let's use this one that I created already. And it's going to go out and provision some computing resources for performing this interactive section of Data Brew on this data set. As you recall from the pricing, it's a $1 per interactive session, and then if you want to actually run this as an ongoing job, then that's billed by the resources that you use. But for now, it's going to spin up some computing resources pretty quickly. It's going to initiate my Data Brew session any minute now. This actually does happen pretty quick. It's not like spinning up an EC2 node or anything like that. And here we go. It's preparing a data frame from that sample data, loading it in from S3. And we're ready to rock and roll here. So you can see that we have this data frame view of that sample data here, where we have how many times each baby name appeared, the gender, some ID associated with it, the actual name itself, and a year field, which is 1880. I thought this was a 2020 data set, but I'm not going to get into that now. Anyway, the idea here is that you can apply these recipes and build them up that transform this data in any way that you want to. And you can run this interactively and download the results. Or you can create a job that allows you to run it repeatedly and even run that on a schedule. So for example, let's say that I only want want to get baby names that start with the letter L for some reason, just as a really simple example. Let's create a new recipe here. So we have this, we can add a step to our recipe. And here's the menu of all those different transformations that you can perform, 250 plus of them. There are column actions. You can rename columns or change their types or move them around or duplicate them or delete them. You can filter things, which we're going to do. You can change the formatting of text fields. There's data cleaning operations here that are built in. So if you want to remove special characters or remove numbers, whatever you want to do, if you need to prep that in ahead of further processing, you can do that very easily with the clean filters. We can also extract information between delimiters. So if you had a field that had delimited data and you just want to extract data between those delimiters, that's easy to do. You could just specify what the delimiters are and where you want to put that column, right? Very easy way of doing that. Also, you can impute missing values automatically. That's kind of a cool feature. So what do you want to do if data is missing? Do you want to just fill it with null or empty values? Do you want to delete the row entirely? Or maybe you just want to fill it with the most frequent value as a placeholder. Sometimes that's the right thing to do. Very easy to do in DataBrew. What else can we do? Invalid values, you can deal with that. You can deal with duplicate values however you want to. You can split columns, merge them together, create new ones based on some sort of a function, unnest, pivot, group by, join, union. Now we're getting into sort of SQL style operations, right? So pretty much anything you could do from a database, you can do in DataBrew. We can scale numeric values. That can come in real handy if you're preparing data for deep learning, right? A lot of times you need to normalize that data before you feed it into a neural network. And these scaling operations make that really easy to do. What else we got? Aggregates, text functions. These are all basically SQL functions available to you. And this kind of fleshes out a lot of those 250 options there. But you can see pretty much any transformation you might want to do is in here. So that's really neat. It allows you a very scalable and powerful engine for transforming and pre-processing data that usually doesn't involve writing any code. So pretty cool. So let's say we want to filter data to just get baby names that start with the letter L. So I'll say filter by condition, and we'll select the name column, and we'll say it must start with L. And I can actually preview that with the preview button here. And you can see that only the baby names that start with L have been preserved. Pretty cool. I can then apply that to the entire data set. And now we have a data set of baby names that start with the letter L. Pretty cool. You'll see there's shortcuts to a lot of these up here in this dashboard. And what can I do? Let's go to Actions. So I can actually download that filtered data as a CSV file, which is neat. Or I can create a new job out of it if I want to run it repeatedly. So that'll take me down to the Jobs tab here. I could create a job name for it, baby names L, whatever you want to call it. And we can set the output settings here. So the file types that you can output right now are kind of limited, but it can be CSV, glue Parquet, Avro, Orc, XML, or JSON. Those are the current output choices. Into the S3 bucket of your choice and the compression of your choice. Snappy gzip, LZ, bzip, or deflate and Brotli. Those are two new ones. Whatever delimiter you want, comma separated, colon separated, tab separated, anything you can imagine here that you might want. And yeah, once you have this, you can actually run that job as a on-demand thing, or you can create a schedule for it. If you go back to the DataBrew console here and go to Jobs, you can click on the Schedules tab, and here's where you would actually create a schedule to run a job repeatedly on some sort of a cron style schedule. So you can do that too. Again, going back to the main pricing tab here, currently those interactive sessions are just $1 per session. But if you want to make a job and run it repeatedly, it's charged at 48 cents per node hour for that processing cost. And if you want to calculate that, there's a handy dandy cost calculator. So that's DataBrew in a nutshell. As you can see, its whole purpose of existence is to provide you a very easy way to pre-process data at a very scalable way and a very quick way without writing any code. And it's a relatively new feature and possibly an alternative to using Glue ETL for you. One more feature in AWS Glue is Elastic Views, and it's so new as of this recording in 2021 that it doesn't actually exist yet. All you can do is register for a preview of it at this time. So don't worry about it being on the exam just yet. It's just too new. We'll spend more time on this once it is on the exam and it's actually been released to the public, but for now, it's just something to have on your radar. It's coming soon. Its purpose in life is to build materialized views that are coming from data sources in Aurora RDS or DynamoDB. So this is kind of a SQL database thing, right? A very specific use case. Those materialized views can then be used by other SQL-style databases, including Aurora and RDS, but also by Redshift and Elasticsearch and S3 and DynamoDB, things that can actually query SQL-style databases. And unsurprisingly, the interface for it will be based on SQL. So it would be just like, building a materialized view from within a relational database. But the value proposition here is that Glue Elastic Views will automatically handle any copying or combining and replicating of data needed to create those views. So often those ETL tasks are kind of the hard part of building and maintaining these materialized views, and Elastic Views will manage that for you. It will continually monitor for changes to your data and continuously update the materialized view as needed automatically. It's also a serverless platform, so there's no servers for you to maintain. This all happens under the hood in AWS. So more to come on Elastic Views. Right now, it's too new to really talk about too much, but just keep it in the back of your head that it's coming. Let's talk about AWS Lake Formation, a relatively new feature. It was announced back in 2018 and really saw a lot of refinement over 2020, and we're just now starting to see it show up in the exam. Lake Formation is built on top of Glue, and it's really meant as a system for making it easier to set up a secure data lake. Their tagline is, it makes it easy to set up a secure data lake in days, which I guess is pretty quick. The things that it manages for you is loading your data from an external source and monitoring those data flows, so it allows you to connect to your existing data sources, whether they're already in S3 or in some on-premises database. It can set up partitions for you, it can help you manage encryption and manage the keys surrounding that, and it can let you set up the transformations associated with that data from the get-go. Again, it's built on top of Glue, so pretty much anything Glue ETL or any of the Glue features can do is available to you. If Spark can do it, then Lake Formation can do it too. It's just using Glue under the hood to apply those transformations. And that includes transforming it into a new format, like a columnar format like Parquet or Orc. That's on the table. Cleaning your data, getting rid of missing rows, whatever you want to do. Anything that we've talked about with Glue, you can do with Lake Formation. It can also help you manage the access control to the data in your data lake. It can help with auditing, and really its purpose in life is to kind of guide you through the process of building your data lake in a secure fashion. So let's talk about it from a more conceptual standpoint here. Basically, you have a big S3 data lake sitting there when you're done, right? So Lake Formation is going to sit alongside that S3 data lake, help you create it, help you maintain it going forward. So it can take as a data source anything in S3 from some relational database that you might have sitting around, or even NoSQL data sources. And those can be on premises as well. It doesn't have to be in AWS yet. So again, the purpose of Lake Formation is to help you set up that data lake, and that data might be coming from someplace else. Within Lake Formation, you can set up all the crawlers and ETL jobs and data catalogs and security and access control, any data cleaning or transformations, including to Parquet or Orc. Again, basically anything Glue can do, you can set up as part of Lake Formation. And once you have a Lake Formation set up, it can then integrate with Athena or Redshift easily, or Redshift Spectrum. So Athena and Redshift can then query that data automatically if you have it all registered in Lake Formation. And a relatively new feature in 2020 is EMR can also talk to Lake Formation directly as well. Pricing. Lake Formation itself doesn't cost anything, but the underlying services do, of course. That includes Glue, S3, EMR, Athena, and Redshift. Normal charges will apply for whatever you build using it. The process for building a data lake using Lake Formation, it's a little more complicated than you might think. It doesn't really do it all for you. This is why they say it takes days and, not just minutes. Basically, you have to start by creating an IAM user for a data analyst role, the person that's going to be using this data lake and building it. You then need to create a Glue connection to the incoming data source, or sources, create an S3 bucket for the lake itself, and then once you've done that, you can register that S3 path in Lake Formation and start granting permissions to it. So this is where Lake Formation starts to be useful. You then create a database within Lake Formation for the underlying data catalog and grant any necessary permissions to it. And at that point, you can start using blueprints to build up workflows. For example, making database snapshots, whatever you want to do to transform that data and get it into your data lake. You then run the workflow and grant select permissions to whoever needs to access the resulting data lake, Athena or Redshift Spectrum, or now it could be EMR as well. That's it conceptually, which is pretty much all you need to know for the exam. Sometimes they like to dig in on these little troubleshooting things and scenarios of things that can go wrong with it. One finer point with AWS Lake Formation is the issue of cross-account permissions. So if you do need to have people across different accounts accessing your data lake and accessing Lake Formation, you need to make sure that the recipient is set up as a data lake administrator. And also take note that AWS Resource Access Manager, RAM, can be a useful tool for managing accounts external to your organization and what resources they can access within your account. Also, there are IAM permissions for cross-account access that would be relevant here as well. Keep in mind, Lake Formation does not support manifests in queries from Athena or Redshift, so that is one thing that can cause errors if you're using a manifest in a query, one thing to keep in mind. Also remember, IAM permissions on the KMS encryption keys are needed for encrypted data catalogs in Lake Formation, and IAM permissions are needed to create blueprints and workflows within Lake Formation. So these are all potential troubleshooting things you might want to know. If you're encountering an error about being able to create a blueprint or a workflow, it's probably an IAM issue. If you're having a cross-account permission issue, you probably need to do something with RAM. So things to keep in the back of your head. Some newer features that are worth talking about with Lake Formation is governed tables and also some new security features. Governed tables is a new thing that supports ACID transactions across multiple tables. So we now can safely concurrently do row-level accesses and updates and deletions without worrying about those multiple users stomping on each other. So ACID means that we have strict transactional guarantees there in place. This uses a new type of S3 table under the hood, so it's still on S3. And once you create that choice of being governed or not, you can't change your mind later on. But it does give you ACID support with your data lake, which is kind of neat, right? I mean, kind of the whole point of using a relational database management system instead of a data lake was that ACID support, and now you don't have to make that trade-off anymore. It also works with streaming data. It doesn't have to be with streaming data, but you can pipe data in from something like Kinesis into AWS Lake Formation into a governed table and actually query that streaming data with ACID guarantees as well. Pretty cool stuff. You can even query it with Athena automatically and just automatically get that ACID support through Athena by using the new governed table feature in AWS Lake Formation. Now, one downside of ACID support on something like a data lake is that there's sort of an overhead that piles up over time for supporting that. I won't get into the details, but it is important to periodically compact and compress that data back down to avoid the overhead of accessing that storage increasing over time. And AWS Lake Formation with governed tables has an automatic compaction feature that will optimize your storage automatically over time. So you don't have to think about that. Even though there is sort of an increasing overhead that piles up as you go, it will take care of that for you automatically with automatic compaction. Also new in AWS Lake Formation is granular access control with row and cell level security. So whether you're on a governed table or an old school S3 table, you now can control access on both the row and the cell level to specific users. So that's an important feature for some applications currently supported now. Now, all of the above features we've talked about do incur additional charges, but they're just based on usage, so you're only being charged for what you're using. Seems fair to me. But those are some of the latest and greatest developments in AWS Lake Formation. ACID support using governed tables that are automatically compacted and optimized for you. And also, we now have row and cell level security for access control. I do want to spend a little bit more time on data permissions in Lake Formation because reportedly this does crop up in the exam in a couple of places. So let's go into a little bit of depth. Lake Formation does make it easier to set permissions on your underlying data in S3. So this is often a way to enforce really fine-grained control. We talked about the new fine-grained access control features in the previous slide, but even without that, we have the ability to restrict permissions all the way down to the column level just using this UI that you see on the right here. It's pretty easy to use. So just by studying this UI screen, you can understand a lot of what the capabilities are. Starting at the top, you can see that you can tie your permissions to IAM users or roles, to SAML users and groups, or to external AWS accounts even. Those are all possible. And you can just build up a list of the different principles that you want to tie a specific set of permissions to. It allows you to use policy tags if you want to. And that can be tied to databases, tables, or columns, and you can base your security based on those tags. That's always a good practice. Or you can just explicitly set permissions based on either a table or specific columns within the table below. And you can see there's a very handy UI there for saying, do you want to let them do selects or inserts or deletes or anything else that you can dream up there for a specific table or even for specific columns on a table. So if you see questions about implementing column-based security on your data lake, lake formation might be the way to do it. Next, let's talk about EMR, or Elastic MapReduce, another very important service in the data analytics world on AWS. What is EMR? Again, it stands for Elastic MapReduce, and what it really is a managed Hadoop framework that runs on EC2 instances. So basically, Amazon took Hadoop and they integrated it with EC2. That means that you can launch a cluster that runs Hadoop using the AWS console. This is a managed framework, but you do have to specify what servers that you want to be running it with, how many instances you want in your cluster, what software you want installed on it, and in return you will actually be able to log into these instances and do low-level stuff with it. So for example, you could say that you want Apache Spark installed on your EMR cluster. So instead of having this totally opaque system like you did with Glue ETL, where you don't see the servers, if you want to get down and dirty and actually have low-level access to Apache Spark and want to be able to have explicit control over the resources that it has, EMR might be for you. You can also include applications such as HBase or Presto or Flink or Hive and more, and we'll talk about those in more depth shortly. If you want to develop code that takes advantage of your cluster on EMR, it offers something called EMR Notebooks, where you can develop and iterate on your scripts on your cluster, just using a notebook environment in your browser. And they've integrated EMR, or integrated Hadoop rather, with AWS at several key points, which we'll also talk about more. So what makes up an EMR cluster? Well, an EMR cluster is fundamentally just a collection of EC2 instances that are running Hadoop. Now, each one of these instances is called a node. Each node has a role within the cluster, which we call the node type. So there are 3 different node types that an instance in an EMR cluster might be performing. One is the master node. You always need at least one of these. So the master node will manage the cluster by running software components to coordinate the distribution of data and the tasks among other nodes for processing. Its job is to track the status of those tasks and monitor the health of the entire cluster. So every cluster will have a master node. You could even create a single node cluster that has nothing but a master node. So a bare bones minimal single node EMR cluster would just have a master node that does everything. The master node is also referred to as the leader node sometimes. Then we have the core node. So the core node has software components that run tasks and store data in the Hadoop distributed file system, HDFS, on your cluster. Or on EMR, it might be EMRFS, which allows you to write data into S3 instead. But the core nodes are what are doing the actual work and distributing that work across the cluster. So the trick here is that your job would be split up across many core nodes potentially, each of them responsible for storing a part of your data and for running the processing on a portion of that data. So a multi-node cluster will have at least one core node. If you're going to distribute your processing, you need at least a core node. Now the third type for EMR is a task node. So this is kind of a newish thing. So a task node has software components that only runs tasks but does not store data in HDFS or EMRFS. They are optional. So if you need to add more processing capacity to your cluster, but you don't need more storage capacity, a task node might be a good choice. And if you think about it, EMR is often using S3 for its storage under the hood, right? So you don't always need to have more storage available to you on an EMR cluster because it's all getting funneled into S3 anyway. So a task node can make a lot of sense on EMR where you don't necessarily need a ton of storage on the EMR cluster itself. So that saves you some money, right? Like you're not paying for all the storage that you're not using. Now the other thing too is that there's no risk of data loss when you remove a task node because it can't write data, right? So you don't have to worry about that. That means that it's a good thing to be using for spot instances, all right? This is something that I can almost promise you'll see referred to on the exam somewhere. The availability of spot instances for task nodes. If you want to cut down your costs on an EMR cluster or add more capacity in a cost-efficient way, A spot instance is a great way to do that because you don't really care if it goes down. It's just being used for extra processing capacity, and the cluster can handle it if that comes in or out as you're processing your jobs. There's no risk of data loss with a task node because they don't store data. So again, remember, a good way to expand your cluster dynamically is by using a spot instance on a task node. A few ways of using EMR. So one is by using a transient cluster. A transient cluster will automatically terminate once all the steps are complete that it's been assigned. So when you set up a transient cluster, you can say, okay, I want you to spin up this EMR cluster that has this kind of hardware behind it, and it's going to run these processing steps that I've defined ahead of time, and then when it's done, shut yourself down. So you can define ahead of time steps in EMR that will load your data, process your data, and store the results, and then when it's done, automatically shut down the cluster. That's what a transient cluster is all about. And obviously this saves money because you're not paying for time on this cluster beyond what you need. So if you do have these sort of one-shot jobs that you need to run once in a while, a transient cluster is a good way to do that, where it will just spin up those clusters' resources, run your job, and then shut down. So good way to save money potentially. However, sometimes you want to basically build a data warehouse that's long-lived. You don't want to be spinning up this thing all the time and shutting it down and losing all of your data in the process, right? So if you want to build basically a data warehouse with periodic processing on some large data set where you can access that data whenever you want or be running jobs on it continuously, a long-running cluster might be more appropriate. So in this case, you would spin up a cluster, with whatever parameters that you specify up front and just leave it running forever. Well, not forever, but until you manually shut it down. And if you do need to add capacity to it later on, you can always spin up more task nodes using spot instances for temporary capacity needs that you might have, like we talked about. If you want to save even more money, you can use reserved instances on these long-running clusters to save even more. If you know you're going to be running this cluster for a long time, then obviously a reserved instance is a good choice for the hardware backing that cluster. So by default, termination protection will be on and auto termination will be off on a long-running cluster. It will try to preserve itself as much as it possibly can. So two use cases here: transient clusters, if you just want to spin up a cluster on demand, run something that you've predefined and then shut it down, or a long-running cluster where you have it running all the time and can access it whenever you want to and keep that around in a more persistent manner. You specify the frameworks and applications when you launch the cluster. So we talked about, for example, running Spark. That would be something that you would select when you're spinning up the cluster ahead of time, and it will automatically install those frameworks and applications that you want when it's being spun up. Once you have a cluster spun up, if it's a long-lived one that's not just running in a transient manner, you can then connect directly to the master node, and from that master node, run your jobs directly. So if you're a command line type of person, you would basically, for example, set up a Spark-enabled EMR cluster, connect to the master node, kick off your Spark driver script, and it would go off and do its thing using the complete power of the cluster. So that's one way of using EMR. Or you can submit steps via the AWS console to EMR. So these steps you can define strictly in a graphical manner through the console, and you can do basic things like processing data in S3 or from HDFS, which is the underlying file system of Hadoop. You can output that data to S3 or somewhere else, but once defined, you can then kick off those steps via the AWS console instead of going through a command line prompt by a direct connection to the master node. So two ways of using EMR. You can log into the master node and kick stuff off, the old-fashioned way, or you can define your steps using the console exclusively and kick off those steps through the console to run on your cluster. So EMR is not just Hadoop running on EC2. They've actually gone through a lot of effort to integrate EMR with the AWS ecosystem at several points. So let's talk about those because they're important to know. So it does use Amazon EC2 under the hood for the instances that make up the nodes within your EMR cluster. So under the hood, you have EC2 instances that are running the nodes on that cluster for you, and they can do everything that EC2 can do. It's also using Amazon VPCs to configure the virtual network in which you're launching your instances. So you're launching the instances for that cluster within an Amazon VPC. It integrates with Amazon S3. So normally on Hadoop, you only have access to the Hadoop Distributed File System, HDFS. But they've extended that with EMR so that you can actually store your input and output data to Amazon S3 instead. And we'll talk more about how that works. Also, it integrates with Amazon CloudWatch, as does pretty much everything, to monitor the performance of your cluster and to configure any alarms that you might need to rig up for the cluster. You can use AWS IAM to configure permissions on EMR, and we'll go deeper on security shortly. CloudTrail can be used to audit the requests made to the EMR service. And AWS Data Pipeline integrates with EMR so that you can schedule and start your clusters as part of a data pipeline. Remember, you can set up these transient clusters that will automatically kick off steps, and with a data pipeline, you can schedule when that happens as part of a larger process. So let's talk more about storage with EMR. So there are several options available to you. One is HDFS. So remember, this is fundamentally a Hadoop cluster running on EC2. And if you want to use the HDFS file system, you can. So that's going to be using the local storage on each instance to distribute the storage across the entire cluster. The way HDFS works is that it stores multiple copies of each file block across cluster instances. That way we have redundancy in case one node goes down. It can recover from that because it always makes sure that your data is copied to more than one place. That way if an individual instance fails, no data is lost. It can just go ahead and reroute things to that other backup copy and start building up a new backup copy. So each file in HDFS is stored as blocks, and those blocks are what is distributed across the cluster. It's not files, it's blocks of data that make up each file. Now by default, the size of a block in HDFS is 128 megabytes, which might be important. However, the thing is that with EMR, that HDFS storage is going to be ephemeral. As soon as you shut down your cluster, you're going to lose all that storage, right? So that's kind of the problem with EMR. It's not necessarily something that you leave running forever like you would with a traditional Hadoop cluster, although you can. But since you're being billed by the minute, you have to remember that as soon as you terminate that cluster, if you have the idea to save some money and stop racking up your bill, which can add up fast with a large cluster, that data is going to go away. And that's a problem, right? So if you're writing all of your output to HDFS and you shut down your cluster because someone wanted to save a few bucks, all that data is gone and you're going to have a very bad day, right? However, you can still use it for caching intermediate results or workloads that have significant random I/O. The nice thing about HDFS is that Hadoop will try to process data where it is stored on HDFS. So it will try to distribute the processing of your data such that the processing of a block happens on the same node where that block is stored. That's a really important optimization that HDFS enables. But it is really kind of a showstopper issue that as soon as you terminate your cluster, it's all gone. So what do? Well, this is where EMRFS comes in. And the idea of EMRFS, or the EMR file system, is to access S3 as if it were HDFS. So with EMRFS, you can write data out just like it were HDFS. You just use a different prefix for where you're writing it out to, S3. And that allows persistent storage even after your cluster terminates. Now, one problem that used to be an issue was the issue of consistency. So what happens if you have multiple nodes writing into the same spot on S3 at the same time? There could be a contention issue there, like who actually gets who goes first, right? So it used to be that there was this thing called EMRFS consistent view. And at this point, I'm not really sure if the exam reflects that this is no longer necessary. So you might still need to know about this. Sometimes the exam lags changes in technology by several months. So I'm still going to mention it here. But it is an option for S3 consistency, where it uses DynamoDB under the hood to track file access consistency for that underlying S3 data store to make sure that if you have multiple nodes from your EMR cluster hitting the same file in S3 at the same time, it will still work. And this actually gets really complicated potentially because if you have a lot of I/O traffic going on there, you might have to tinker with the read-write capacity on the underlying DynamoDB instance to get it to work reliably. Kind of a pain. Fortunately, Amazon realized that this was a pain, and new in 2021, S3 itself is now strongly consistent. So now that S3 guarantees consistency, we don't need to worry about EMRFS consistent view anymore. So it's no longer an issue. It just works magically now. Now, we are still giving up the optimization of processing data on the same machine where it's stored. Obviously, S3 is going to store this data somewhere else across the network. So in theory, it's not quite as fast as using HDFS, but in practice, it's still pretty darn fast. S3 can be pretty quick, and it's all in the same data center. So in practice, you can still build large-scale efficient applications using EMRFS that's using S3 instead of the HDFS file system that's built into Hadoop. So that lets you run Hadoop applications using S3 as a persistent data store so that when you terminate your cluster, your data does not go away. Other options are using the local file system. Obviously, that's also going to be ephemeral and not backed up anywhere either. So although it's going to be fast, there's not much of it, and it's only suitable for temporary data. So if you want to have temporary buffers or caches, fine, you can write them out locally. Just make sure you're not depending on that sticking around for any length of time. Also, Elastic Block Store for HDFS. You could use EMR on EBS-only types like M4 or C4 by using that feature. But again, just like local storage, your Elastic Block Store is going to be deleted when your cluster is terminated as well. So not really giving you a whole lot beyond HDFS there. But if you don't really have a local file system because you're using an EBS-only instance type, it can still use EBS for that local storage and for backing HDFS. Now, EBS volumes can only be attached when you're launching a cluster, remember too. So you're not going to be able to expand that storage capacity after the fact, which is another reason maybe to avoid it. Keep in mind as well that if you manually detach an EBS volume while it's running, EMR will treat that as a failure and it will automatically replace it. So it is resilient to that failure mode at least. But again, if you do want persistent storage that's going to last after your cluster is terminated, you kind of have to use EMRFS with S3 for that. So let's talk about the promises that EMR makes to you. First of all, let's talk a little bit about pricing. So EMR charges you by the hour. So the longer you leave your cluster running, the more they're going to charge you. And this can add up really fast if you're using expensive instance types like GPU instances and things like that. So keep that in mind. If you can run your task as a set of steps that automatically starts and stops the cluster when it's done, you'll save a lot of money that way. If you need to leave your cluster running 24/7 though, it can get expensive and you need to be mindful of that. As far as failure goes, if a core node fails, EMR will automatically provision a new node for you under the hood, so you don't need to worry about that at least. And that will just automatically pick things up where it left off. If you need to resize things, if you need to add capacity though, probably the best way to do that is by adding or removing task nodes on the fly. Now remember, task nodes are kind of like core nodes, but they have no storage capacity of their own. There's no HDFS capacity associated with a task node. Now normally you don't care because you're probably using EMRFS to talk to S3 under the hood so that your data is more persistent, right? But even if you are using HDFS, you can still use task nodes to increase your processing capacity if you don't need to increase your storage capacity at the same time. A good example of this is for, let's say you're running some e-commerce website, like you're at Amazon or something, and you need to have this huge surge of data coming in associated with Christmas time or something like that. Let's assume that your storage is okay, but you need to process that data a lot more. There's a lot more CPU time involved in that processing. You could just temporarily add a bunch of task nodes to your EMR cluster to handle that surge in processing, and then later remove those task nodes when that surge is passed. So adding and removing task nodes on the fly is a good way of dealing with temporary surges in processing CPU needs. Remember that. You can also resize a running cluster's core nodes without much trouble, and that can be a way to increase both your processing and HDFS capacity. So, if you do need to increase both your processing time and your storage capacity, and you're not using something like EMRFS where your storage is somewhere else anyway, you could resize the core nodes as well. It's also possible to add and remove a core node on the fly. This is kind of a new thing, but it's not always a great idea. If you do remove a core node, remember you're removing that underlying storage as well. So if you're using HDFS capacity, you are risking data loss by removing a core node on the fly. So just because you can do it doesn't mean you should. Again, just to recap here, generally speaking, if you need a temporary increase in processing capacity, adding task nodes is a good way to do that. If you do need to add storage capacity as well on HDFS, you can resize a core node. You can also add and remove core nodes on the fly, just like you can with task nodes, but a little bit more risk with data loss if you're doing that on core nodes versus task nodes. So let's talk a little bit more about how managed scaling works in EMR specifically. So managed scaling was actually introduced in 2020. Before that, they called it EMR automatic scaling. That was the old way of doing it. And it created custom scaling rules that were based on CloudWatch metrics. So, prior to 2020, or even in the first half of 2020, this is how automatic scaling in EMR worked. You would monitor CloudWatch metrics automatically, and you could automatically add or remove capacity to your EMR cluster, but it was limited to instance groups only. So you couldn't really mix and match different instance types with your automatic scaling. That changed in 2020 with EMR managed scaling. So now, in addition to supporting instance groups, it can also support instance fleets. So it can scale up and down your Spot, your on-demand, and your regular instances in a savings plan within the same cluster. And this is actually available for Spark, Hive, or Yarn workloads in EMR specifically. So when you're scaling up in EMR managed scaling, the way it works is that it will first try to add core nodes, and then if it hits the limit on that, it will add task nodes, and it will just do that up until the maximum number of units that you specify. So the configuration you provide in managed scaling is what's the maximum number of core nodes I want to add, what's the maximum number of task nodes I want to add. If it needs to scale down, if it sees some sort of CloudWatch metrics that suggests that you have too much capacity, it will start by removing the task nodes and then by removing core nodes, again, no further than the minimum constraints that you set. So you can say, I want no fewer than this many task nodes, I want no fewer than this many core nodes, and managed scaling will honor that as it scales down as need be. Also, note that Spot nodes will always be removed before on-demand instances with managed scaling. Okay? So that's managed scaling and how it works. Basically, you specify a max number of units and a minimum constraint on the number of nodes. Core nodes and task nodes are both managed, and you can apply that across a fleet and not just an instance group. So let's start talking more about the applications you'll be running on your EMR cluster. So fundamentally, it's a Hadoop cluster. So let's talk about Hadoop in a little bit more depth. What is Hadoop? Well, the Hadoop architecture comprises several modules, these modules here. They make up what we call Hadoop Common or Hadoop Core. This is kind of like the basis of Hadoop itself, these three components that you see here. These are the libraries and utilities that are required for other Hadoop modules to build on top of. It provides all the file system and operating system level abstractions that we need on top of your cluster and the jar files and scripts that are needed to actually start Hadoop itself. So at the bottom here, we have the Hadoop Distributed File System, HDFS. This is a distributed, scalable file system that stores blocks of data across instances in the cluster. It stores, again, multiple copies of those blocks on different instances to ensure that no data is lost if an individual instance fails. Now on EMR, this is ephemeral storage. Your data on HDFS will be lost upon terminating the cluster. But it is still useful for caching intermediate results during MapReduce processing, or for workloads that have significant random I/O. Or if you intend to leave your EMR cluster running forever, well, fine, go for it. You can use that for persistent storage, but it's not going to be cheap. Sitting on top of HDFS is Yarn. That stands for Yet Another Resource Negotiator. And it's basically an abstraction level that was added in Hadoop 2.0 between MapReduce and HDFS. And as we'll see, that allows us to run replacements for MapReduce that are better on top of HDFS. So basically, it allows you to centrally manage your cluster resources so that we can have more than one data processing framework, and we're not tied directly to MapReduce, which used to be the case back in Hadoop 1. Now, the core data processing framework that's part of Hadoop itself is MapReduce. It's still out there today. It's a software framework for easily writing applications that process vast amounts of data in parallel on large clusters of commodity hardware in a reliable, fault-tolerant manner. You can probably tell that's the official definition, right? But basically, why is it called MapReduce? Well, it's made up of mappers and reducers. So a map function in MapReduce will map data to sets of key value pairs. And these are basically the intermediate results of your processing. So it's basically parsing your data, extracting the data that you need to process, and organizing them as key value pairs. Then reducer functions combine those intermediate results, apply additional algorithms to them, and produces your final output. So generally you have mappers and reducers that extract data, reduce it down to the final answer that you want, and output that somewhere. So that's originally how you did distributed file processing on a Hadoop cluster. But these days, it's largely supplanted by Apache Spark because it's a lot faster and a lot more extensible and can do more stuff. We'll talk about Spark next. Let's talk about a newer feature in EMR, EMR serverless. It's going to be new in 2022. Works pretty much the same idea as EMR. The difference is that the intermediate step of defining just how much capacity we need is removed from us. So we can let EMR just decide for itself how many nodes it needs in the cluster to actually do what we want it to do automatically. So to use EMR serverless, we just start by choosing our EMR release and runtime, Spark, Hive, or Presto, just like we would before. And then we just submit queries and scripts to our EMR serverless instance via job run requests. So rather than, logging into your master node directly, it's serverless. So, you just want to interact with it indirectly. You'll give it a path to some S3 thing somewhere that says, this is where my script is. It'll reference data from S3. And you just feed that script or that Hive query into it from S3 to your serverless server. And it will automatically, in theory, figure out how much capacity you need to actually successfully run that job. So EMR will manage the underlying capacity for you. But if you want to think about the underlying capacity, you still can. And this might be a good idea in a lot of situations. So if you know that your job requires a few resources, you can specify that up front. You can specify the default worker sizes up front, and you can also pre-initialize your capacity. So instead of starting from nothing, you can tell EMR serverless, hey, I think the base capacity I'm going to need is this many nodes that are this size, and start from there. That'll help you out. Otherwise, it will try to compute it for you automatically. And even if you do start off with a base setting of a pre-initialized capacity, it will analyze the resources that are actually needed for your job and adjust that accordingly and schedule workers as you need them and deschedule them as you don't need them. As of right now, it all works within the same region across multiple availability zones, of course, so your serverless cluster will be within one region. So why is this such a big deal? Well, you no longer have to figure out how many workers you need, right? So a really big pain point in things like Apache Spark is that if you guess too small, if you don't have enough resources for a job, you're going to end up running out of memory, your job will just fail halfway through, and it can be a very time-consuming and expensive process to figure out how much capacity I really need, because it's really not a very good way of figuring that out ahead of time. So EMR serverless is solving that problem. So that's actually kind of impressive if you ask me. You'll automatically provision the capacity you need for your job. So you don't have to worry about it, which is really a big deal. You can focus on the scripts and what you're trying to do instead of figuring out how much capacity you need to do it. And like I said, it's not really serverless in the way of some other serverless servers where you really don't think about the servers at all. Under the hood, you're still using Spark or Hive or Presto, and those technologies kind of assume that you have some knowledge of what's going on at the worker node level or the driver level, right? So if you still want to configure Spark down to that level, you're still going to have to think about the worker nodes and their capacities. The difference is you don't necessarily know how many of them you have, and you don't necessarily know where they are. How do I go about using EMR serverless? Well, you start off with an IAM user that you are going to be interacting with it from, and that will work with the AWS CLI. So your user will invoke the CLI to create this serverless cluster. For now, only the CLI is supported. I'm sure that will change pretty soon. I can't imagine that they wouldn't have console support and SDK support sometime in the future. But for now, it's command line interface only. You then need to set up a job execution role in IAM for the job itself, and that makes sure that your job has permission to access Amazon AWS EMR serverless, as well as any permissions that it needs to access your scripts in S3, any data that it needs to access in S3. If you're doing something with Spark SQL, you might need access to Glue for Glue metadata stuff, or any KMS keys that you might need for any security that you've set up as well. With that in hand, you can then create a EMR serverless application using Spark, Hive, whatever you want, and then just feed it in your job through an EMR job request there. So you give it a link to your Spark script, your Hive query, whatever it is. Might look like this. So here's an example of a command line to invoke an EMR serverless job. We're just saying AWS EMR serverless start job run, passing in our application ID, the execution role that we talked about earlier with a path to that. And then under job driver, this is where it gets interesting. We're saying under Spark submit, the entry point is this path to the script itself. We can pass in arguments to that entry point as well if we want a parameter to where it should put its output, for example. And we can also override the Spark submit parameters as well. So if you wanted to submit parameters to Spark itself on the command line of Spark submit, you can specify that here too. So again, even though we're calling this serverless, I'm still thinking about here how big my executor cores are, what are my driver cores look like, things like that. So you still have that level of control here, even if you're handing off the actual capacity and the amount of nodes off to EMR serverless. Also, you can send configuration overrides that are specific to EMR serverless. In this example here, we're saying that we want to output our CloudWatch logs to this path in S3. When we're done, we get our output and our logs wherever we said to put them, and that's it. You just shut it down when you're done, and it's just like EMR. Let's talk about the life cycle of an EMR serverless application real quick here. So you start off by explicitly creating your application through a command currently from the CLI. If that succeeds, then great, you created your application. If not, it will automatically terminate. From that point, you have a new application sitting there that you've created. You might choose to terminate it right away. That's an option. Not sure why you would do that, but normally you would proceed to issue a start command to start your application. And that will kick it off and actually run it. Once it's started, it will either succeed and then move to the stopping phase when you're done, or it will fail and move to the stopping phase automatically. Once it is successfully stopped, you can either run it again, go back to start, or go to the terminated phase and shut it down when you're done. Now, I want to stress that this is not all happening automatically. I need to call commands through the API, such as create application, start application, stop application, and when I'm done, delete application to make this all happen. So I've had students contact me saying, hey, you use EMR in a lot of your courses, and you're always warning us to remember to shut down your cluster when you're done so you don't get charged for them unexpectedly. Should I just use EMR serverless so I don't have to think about it? No, that does not solve the problem. It helps because you will automatically, not be using any more capacity than you need, but you still need to explicitly delete your application when you're done with it. If you forget to do that, you will still be billed for that serverless application, even if it's sitting there doing nothing. Okay, so don't think that EMR serverless is an excuse to get lazy in managing your resources. You still need to think about explicitly starting and stopping and terminating that cluster when you're done. EMR serverless just means that it's thinking about the capacity instead of you, but you still need to manage that capacity to some extent yourself. Let's talk a little bit more depth about pre-initialized capacity on EMR serverless. So here's an example off to the right here of what that might look like from the command line. You see here we have an initial capacity block here that we didn't have before. We're saying that we want to start off with 5 drivers with a specific resource configuration of a CPU type and the memory that each one has available to it. Also for the executor nodes, we're saying we want 50 of them to start with 4 vCPUs apiece and 8 gigabytes per executor as well. So, this lets us say how many processes do I want to power my application. It's still EMR serverless's job to figure out where those processes are running and the capacity needed to actually make it happen. But you can give it a hint like this to say, hey, I know this is a pretty demanding job. I want to start with 50 executors. Go figure out how to make that happen. But just to make things go more smoothly and make sure that I have enough capacity out of the gate, I want you to start from this point. There's also a maximum capacity argument being sent here as well. I want to say that I don't want to use any more than 400 virtual CPUs and no more than 1 terabyte of memory. So that's a pretty good safeguard to have in place in case you do something silly that just wants to use infinite resources. That will be a little bit of a safety net for you there. One note from the documentation, and this does look like the kind of thing that I could imagine seeing on the exam at some point. Remember that Spark adds a 10% overhead to any memory requested for drivers and executors. So make sure your initial capacity request takes that into account. Make sure you're requesting at least 10% more memory than your job is actually requesting. Some notes on security with EMR serverless. It's pretty much the same thing as EMR. For storage, if you're using EMRFS, under the hood, that's S3. So, server-side or client-side encryption on S3 at rest is going to be there for you. For in transit, TLS will be there for you between the EMR nodes and S3. If you're writing directly to S3, obviously all the security that comes with S3 is available to you as well. SSC S3, SSC, KMS, whatever you want to use. For any ephemeral storage on the local disks of your nodes, those are encrypted as well. And in transit, any communication between the driver nodes and executors is also encrypted automatically. If you're using Hive, any communication between the Glue Metastore and EMR is also encrypted in transit using TLS. And a quick note from the documentation here I wanted to pass along. Remember that if you are using S3, you can force HTTPS on in-transit traffic to S3 using the AWS Secure Transport Policy. So we've talked a lot about Apache Spark kind of in passing in the context of Glue ETL transforms, which uses Spark under the hood, and in the larger context of EMR, which can run a Spark application hosted on your EMR cluster. So let's go into more depth about how it works. So Apache Spark is an open source distributed processing framework, commonly used for big data workloads. And as you can see in this diagram, it sits alongside MapReduce as sort of a replacement for the analysis part of this stack. So thanks to Yarn, we can swap out MapReduce for something better. MapReduce was great 10 years ago, but these days Spark outperforms it by quite a bit. And that's because Spark has in-memory caching. It does most of its operations in memory instead of hitting disk or going across the network. And it also has a query execution optimizer. So it can actually look at a complicated SQL query and optimize that to make sure that you have this really optimal directed acyclic graph that runs your query in the most efficient manner possible. So it's not limited to the map and reduce paradigm. It can do more complex operations more efficiently. And it can really be orders of magnitude faster than MapReduce as a result of that. As a result, you really see Spark being used these days and not so much MapReduce. Spark can be written using Java, Scala, Python, or R. I'd say Python and Scala are the more popular choices there. Spark itself is written in Scala, by the way. And the good thing about Spark is that you can really reuse your code across different applications. So because of its software architecture, all these different modules have a common interface. So it's very easy to take the same snippet of code and use it for different kinds of applications, which saves you a lot of work. You can use it for batch processing, which is kind of where it all started. It's also possible to do interactive queries with Spark. It does expose a JDBC interface if you want to, so you can connect to it and just query it directly using Spark SQL. And it has real-time analytics capabilities, machine learning capabilities through the MLlib library, and it can do graph processing as well through GraphX. And by graph processing, we don't mean charts and graphs, we mean information graphs, like a social network, that kind of a graph. It also has Spark streaming and structured streaming, which allows us to process data in real time as it's received from a stream of data, and that integrates on EMR with Kinesis or Kafka. Now, Spark is not made for OLTP. It's not built for throwing thousands of transactions per second against it from some, external-facing website or something like that. It's an OLAP thing. It's meant for running longer-lived queries that might take a few seconds or minutes or maybe even longer to complete. So it's really for analysis, for OLAP applications, not for OLTP. Remember that. How does it work? Well, here's what the Spark architecture looks like. Spark applications are broken up into individual processes that run across your cluster. So at the heart of it all is a Spark context called your driver program. This driver program coordinates all these other processes through your cluster manager, which might be Spark's own built-in cluster manager, or in the case of EMR or a Hadoop cluster, Yarn, yet another resource negotiator, the cluster manager that's built into Hadoop. But you can run a standalone Spark cluster as well. That doesn't depend on that. And then we have the executors that are doing all the grunt work. So the executors run all the computations and store the data associated with your job. And remember, in EMR, that might be running on a core node that has HDFS capability or a task node that does not. The Spark context is responsible for sending application code to those executors and sending individual tasks to those executors to complete. Spark is made up of various components. So at the root of it all is Spark Core. This is the foundation of the platform. It's responsible for memory management, fault recovery, scheduling, distributing and monitoring jobs, interacting with your storage system, which might be HDFS or EMRFS or something else. And it also supports all the guts needed to talk to Java, Scala, Python, or R scripts. Under the hood at this low level, it uses something called the Resilient Distributed Dataset, or RDD, but probably don't need to know that for the exam. On top of Spark Core are four main systems. One is Spark SQL, and this has evolved into really a fundamental piece of Spark these days. Spark SQL is a distributed query engine that provides low latency interactive queries up to 100 times faster than MapReduce. And it can support various data sources and formats like JDBC, ODBC, JSON, HDFS, ORC, Parquet, or HiveQL if you're going to be querying Hive tables. But the important thing about Spark SQL is that it introduces what's called a dataset object, or in the world of Python, a data frame. And basically this allows you to treat your data in Spark as a giant database table and query it just like it were one. So that's really the power of Spark SQL. It kind of gives us this SQL-style interface to our underlying data on the EMR cluster. We also have Spark Streaming. Spark Streaming is a real-time solution leveraging Spark Core's fast scheduling capabilities to do streaming analytics. So it used to be that data was ingested in mini batches, but these days with structured streaming, we can actually do real-time streaming and real-time processing of data using data sets. And again, it's really cool that we can use the same code that we wrote for batch processing and adapt that to streaming very easily using the architecture of Spark. It improves your productivity because you can reuse that code very easily, and it supports data from sources like Kafka, Flume, or HDFS and ZeroMQ. Used to have built-in support for Twitter, but that's more of an add-on thing these days. They kind of deprecated that. MLlib, very important feature there. It's a library of algorithms for doing machine learning on data at large scale. So they figured out a way to distribute the processing of various popular machine learning algorithms. Pretty much all the ones that you would need to use in practice are available for you, so that's really amazing. Regression, clustering, classification, collaborative filtering, pattern mining, it can do it all. And it can read from any data source that Spark can read from, HDFS, HBase, or anything Hadoop can talk to. So just like Spark itself, you can write your MLlib applications using Scala, Java, Python, or R. But it's really cool that we have a way finally of doing complex machine learning algorithms on massive data sets where you're not limited by the capability of a single machine. They've cracked the code on how to distribute that processing. Finally, we have GraphX. Again, that's a distributed graph processing framework built on top of Spark. It provides ETL, exploratory analysis, and iterative graph computation to allow you to interactively build and transform graph data structures at large scale. It's very flexible, but honestly, it's not very widely used. It's kind of fallen into disrepair lately in Spark, so you're not likely to see a whole lot about GraphX anywhere. It's been supplanted by third-party solutions for the most part these days. Let's talk a little bit more about Spark Streaming and structured streaming in particular, because this is a very exciting and widely used part of Spark these days. So Spark applications generally use what we call a data set within their code. And a data set is just basically a giant table of data. So you can just treat your data on your cluster like a giant database table. And we kind of have this sort of trend in the world of data analytics where SQL has become sort of the lingua franca of all these systems. So pretty much everything talks SQL these days. And with structured streaming, that's still the case. You can basically treat your data as an unbounded table where new rows are getting added all the time from your data stream. So it's just that simple. You query it in the same way that you would query a batch process data set, but with structured streaming, it just keeps on growing over time. Now, there are some extra features added to it to allow you to window those queries. So if you want to restrict that to, say, the past 1 hour or whatever it is, you can do that. You see here in this example here, we're reading in a stream of JSON data from S3 in the logs directory there. We're grouping that by their action field. And we're establishing a window over the past 1 hour and just counting them up in this example. We then output that result through the JDBC interface to some MySQL database somewhere. So you can kind of get an appreciation of the power of structured streaming here. With just these 2 lines of code, we've said, go and monitor the logs coming into this S3 bucket in JSON format, add them up over the past 1 hour, and write the results every hour out through JDBC to an external MySQL database. So how cool is that? That's a very complicated operation with just 2 lines of code. Let's talk about Spark Streaming in a little bit more depth. So Spark applications, like we said, usually use something called a data set in their code to refer to your data. And a data set is treated very much like a database table. With Spark Streaming, and structured streaming in particular, you can basically picture your streaming data as a database table that just keeps on growing forever. So as new data is received by the stream, it just keeps adding more and more rows to that virtual database table in the form of a data set. So you can query this data using windows of time. And if we look at this example here, What this code is doing is saying, let's monitor all the stuff that's being thrown into a logs bucket in S3. And this action with a 1 hour window over time means that we're going to be continually counting up the records being received in that bucket over the previous 1 hour. And then we're going to turn around and write those counts using JDBC into some external MySQL database. So the amount of code you have to write for something like this is actually pretty trivial. And that's kind of the power of Spark streaming and structured streaming in particular. Yes, you have to write code, but generally it's very simple code. And you can rely on Spark to manage all the dirty work of making sure that you're getting your stream data reliably and distributing the processing of that stream across your entire cluster reliably. You just focus on the logic of what you want to do, while Spark streaming takes care of all the nasty bits of making sure it's happening in a reliable manner. You can also integrate Spark streaming with Amazon Kinesis. And I mean, there's nothing really magical about integrating Spark streaming with any other system because it's all code, right? And with code, you can do anything. So it turns out somebody has written a library for Spark streaming built on top of the Kinesis client library to allow Spark streaming to import data from Amazon Kinesis data streams. And you just have to plug in that library and code against it, and you can treat Kinesis as any other stream of data coming into a data set in Spark structured streaming. So for example, you might have some Kinesis producers, say a bunch of EC2 host generating logs that are pumping data into a Kinesis data stream. You can then integrate that using the Spark dataset integration code as any other dataset coming into Spark streaming and process it across the entire cluster on EMR using Apache Spark. You can also integrate Spark with Redshift. We haven't talked about Redshift yet, but basically it's a massive distributed data warehouse that's offered by AWS. And like there's a Spark Kinesis package, there's also a Spark Redshift package, and that allows Spark to treat datasets from Redshift just like any other SQL database. So it just makes Redshift look like any other SQL data source to Apache Spark. And again, you can use the power of Apache Spark across your entire EMR cluster to transform and process that data in any way you want in a highly distributed and scalable manner. So that's a good way for doing ETL on Redshift using Apache Spark, for example. Imagine, if you will, that we have, say, a bunch of airline flight data residing in a huge data lake that's stored in Amazon S3. I could, for example, deploy Amazon Redshift Spectrum on top of that data in S3, which will provide me with a SQL interface on top of that data that lives in S3. Now, using the Spark Redshift package, I can then spin up an Apache Spark cluster on Amazon EMR and use that to perform ETL on that data that's residing in S3 through Amazon Redshift, because Redshift just looks like any other SQL data source to Apache Spark. So by integrating Redshift with Spark, I can distribute the processing of that huge data set sitting in S3 and maybe turn around and put that process data back into another Amazon Redshift table for further processing. Maybe I'm doing something like preparing that data for some machine learning algorithm that's going to be used down the road, and that machine learning algorithm can use that prepared and transformed data in that new Redshift table that I've produced from my Spark job. Another important piece of the Hadoop ecosystem is Apache Hive. This comes up a lot on the exam and in life in general, really. So Hive is basically a way to execute straight up, well, almost SQL code on your underlying unstructured data that might live in Hadoop Yarn, or S3 in the case of EMR. Hive sits on top of MapReduce to actually figure out how to distribute the processing of that SQL on the underlying data, and alternately there's another engine called Tez that can take the place of MapReduce. Tez is kind of like Apache Spark in that it uses a lot of in-memory directed acyclic graphs to accelerate things, so often you'll see Hive being used on top of Tez instead of MapReduce. Like I said, MapReduce has kind of fallen out of favor these days for better technologies. But the important thing to know is that Hive basically exposes a SQL interface to your underlying data stored on your EMR cluster. Why would you use Hive? Well, the main advantage is that it uses a very familiar SQL syntax. It's not exactly SQL, technically it's called HiveQL, but it's really close to SQL. And it does have an interactive interface, so you can just log into your cluster and from a little web page type in your SQL queries and Hive will just go off and do it. It's very scalable, of course, like anything else on a cluster. It works with big data, but it's really most appropriate for data warehouse applications and OLAP applications. Even though it is interactive, it's not that fast, so you're still going to be using it just for easy OLAP queries trying to extract meaning from large data sets. But it's going to be a lot easier and a lot faster than trying to write MapReduce code or even trying to write Apache Spark code for that matter. If you just need to do really quick, high-level SQL interactive queries of your data just to sort of explore things, Hive is a great tool for that. Hive is obviously highly optimized, and it's also highly extensible. It offers user-defined functions, so you can extend HiveQL however you wish to, and it also exposes a thrift server and a JDBC and ODBC driver, so external applications can communicate with Hive from outside of your cluster, analytics applications, web services, whatever you might have. Just keep in mind, though, that Hive is not really for OLTP, so you shouldn't be writing a web service that hits Hive continuously hundreds of times per second or anything like that, trying to get results back very quickly. A topic that comes up a lot on the exam is the Hive metastore. So at the end of the day, Hive is trying to impart structure on unstructured data. It's basically sitting on top of, a mess of CSV files or something that you're storing on HDFS or EMRFS or what have you on your cluster. So somewhere it needs to store the information that imposes structure on that data and says, this is what the different columns in this raw data mean. These are the column names. These are their data types. And that information is stored in the Hive metastore. You can take a look at an example here that's being created here. So this is how we might create a structured ratings table just based on raw ratings CSV data. You can see by saying create table ratings, we're defining the column names and data types for each column of that information. We're saying how the actual data is delimited and terminated and the format that it's stored in and where it is actually located. So all that information has to be stored somewhere, and that's what we call the Hive metastore. It will refer to this information as you try to refer to this underlying CSV data as a SQL table. Now here's where things get interesting. By default, the Hive metastore is just stored in a MySQL database on the master node of your cluster. So it needs to be in one place so everybody can get to it and have a consistent view of how this data should be interpreted across your cluster. But obviously that's not great, especially if you're going to be shutting down your master node or something happens to your master node. Hive therefore offers the ability to have an external metastore that you host outside of the cluster somewhere or on some other node within it maybe. And that offers you better resiliency and integration. However, it also offers an opportunity to store that metastore in alternative places. So you might think to yourself, a Hive metastore sounds an awful lot like a Glue data catalog. And you're right, they serve the same function. They're basically maintaining structure information on unstructured data. How do I map this unstructured data to table columns and names and data types that will allow me to treat that data as a straight up SQL table? So it turns out it's actually possible to store your Hive metastore within AWS Glue data catalog itself. So you can have an AWS Glue data catalog that serves double duty as a Hive metastore, and that allows you to centrally locate your metadata for your unstructured data and expose that directly to Hive, where Amazon EMR can get to it, but also expose that same metadata to Amazon Redshift, Amazon Athena, or what have you. And ultimately, that can all refer to underlying data stored in S3, but use that metadata stored in the Glue data catalog to impart structure on it. So that allows you to centralize your metadata in one place, not just for Hive, but for everything else that requires metadata in the AWS ecosystem. It is also possible to store your Hive metastore on an external Amazon RDS instance or Amazon Aurora. Talk about that more later on as well. But basically, RDS is a AWS service that allows you to spin up a database in the cloud. So instead of storing your Hive metastore on a MySQL database on your master node, you can choose to store that in an external RDS database instance that will be more persistent. So even if you shut down your cluster, that metastore will survive in your RDS database. So study this diagram. It is important to understand the intricacies of how the Hive metastore can interact with Glue data catalog and with RDS, because that will come up on the exam. Hive and AWS also integrates in other ways. So for example, you can integrate it with S3 in many different ways. Using Hive with EMR provides you with the ability to load table partitions automatically from S3. So you might recall that you can store your data in S3 under different subdirectories. For example, year, then month, then date, then hour. Those are going to be translated into table partitions. And you can do that automatically with Hive on EMR. You can just type in alter table recover partitions, and that will easily import tables concurrently into many clusters without having to maintain a shared metadata store. Also, using Hive with Amazon EMR provides you with the ability to specify an off-instance metadata store, which we already talked about in the previous slide. And when you write data to tables in Amazon S3, the version of Hive installed in EMR writes directly to Amazon S3 without the use of temporary files. So you can write directly to S3 using Hive's extensions on EMR. The special version of Hive installed on EMR also allows you to reference resources such as scripts for custom map and reduce operations, or additional libraries located in Amazon S3 directly from within your Hive script. So you can store your scripts and external user functions in S3, and Hive on EMR can pick that up directly. Hive on EMR also integrates directly with Amazon's DynamoDB, so you can process DynamoDB data using Hive as well. To do that, you need to define an external Hive table based on your DynamoDB table. You can then use Hive to analyze the data stored in DynamoDB and either load the results back into DynamoDB or archive them into Amazon S3. So this allows you to copy data from a DynamoDB into EMRFS or HDFS and vice versa. And using Hive on EMR, you can perform join operations between DynamoDB tables, which is kind of interesting. Let's briefly talk about Apache Pig. That is also an important part of the Hadoop ecosystem that comes pre-installed on Amazon EMR. So Pig arose as sort of an alternative interface to MapReduce. So it recognizes that writing code for mappers and reducers using MapReduce takes a long time, and Pig introduced instead a language called Pig Latin. This is basically a scripting language that lets you use SQL-style syntax to define your map and reduce steps. So instead of writing Java code for MapReduce code, it's sort of an abstraction on top of that allows you to use more of a high-level scripting language, in this case called Pig Latin. It's kind of an older technology, but it still comes up on the exam, and it's still a popular thing that some people use. Like Hive, it's also highly extensible with user-defined functions, so you can expand on Pig's functionalities in any way you want to if you're willing to write the code for it. Also like Hive, Pig sits on top of MapReduce or Tez, which in turn sits on top of Yarn, which in turn sits on top of HDFS or EMRFS in the case of Amazon EMR. Now, you're never going to be asked to actually write or understand code on the exam, but if it helps you understand what Pig Latin's all about, I put a little code snippet here of some Pig Latin code that will analyze some ratings data that sits on HDFS someplace. So a little example of some Pig Latin there. You can see it's pretty high level. It looks a lot like SQL, but it's not exactly SQL, so there is some learning curve to it. But once you get the hang of it, it's not too bad. Pig and AWS integrate in several ways. Just like Hive, they have extended Pig to be a little bit more EMR friendly. So for example, Pig is not limited to HDFS when you're running it on EMR. It can also query data on S3 through EMRFS. And like Hive, it has the ability to load jars and scripts that are stored externally on Amazon S3 directly. But that's pretty much the extent of Pig and AWS integration. Beyond that, it's straight up Pig. Again, kind of an older technology, but you just need to understand what it is and the applications that it's meant for. It's basically a higher level alternative to writing MapReduce code. Not quite SQL. It's basically a scripting language that looks a lot like SQL, but it's very highly distributed and allows you to analyze your code in a distributed manner. Another piece of the Hadoop ecosystem that comes pre-installed on EMR is HBase. HBase is a non-relational database that's designed to work on petabyte scale data that's distributed across your entire Hadoop cluster, on EMR or any Hadoop cluster for that matter. And like Hadoop itself, it's based on Google technology. So Google published a paper called Bigtable, describing their similar system used within Google. For them, it was built on top of the Google file system, but for us, it's built on top of HDFS. So basically, you have unstructured data spread across your entire Hadoop cluster. HBase can treat that like a non-relational NoSQL database and allow you to issue fast queries on it. The reason it's so fast is because it operates largely in memory. So it's not doing a bunch of disk seeks when it's doing its queries. It's storing that stuff in the memory spread out across the entire cluster. Also, it integrates with Hive, so you can use Hive to issue SQL-style commands against data that's exposed through HBase, which is kind of interesting as well. If HBase sounds a lot like DynamoDB, that's because it is. They're both NoSQL databases intended for the same sorts of use cases. So how would you choose between using DynamoDB and HBase if you're going to be using EMR and storing your data on an EMR cluster? Well, if you're committed to using AWS services anyhow, DynamoDB does offer some advantages over HBase. For example, DynamoDB is fully managed and is a separate system that automatically scales itself. So you're not going to be tied to this managed EMR cluster for the scale of your HBase database. DynamoDB is a separate beast where Amazon manages all the scaling of that for you. So that's a big advantage for using DynamoDB instead of HBase on an EMR cluster. EMR is not a serverless solution, but DynamoDB is. So they serve much the same purpose. So all things being equal, DynamoDB has a pretty big advantage there. DynamoDB also offers more integration with other AWS services. and integration with AWS Glue. So if you're going to be using a lot of AWS services, you're going to find that using DynamoDB instead of HBase is going to offer up a lot more possibilities to you. There are some situations, though, where HBase might be the right choice. First of all, if you're not married to AWS and you think you might want to actually move off to a separate Hadoop cluster outside of AWS at some point, HBase would be a more intelligent choice there. But it's also better at storing sparse data. So if you have data that's just really scattered across your entire cluster, HBase tends to be able to deal with that better than DynamoDB. HBase is also really good for high-frequency counters because it offers consistent reads and writes a little bit better than DynamoDB does. And that's not really necessarily a big scale operation where you need a massive cluster to store that data necessarily. So the scaling concerns that DynamoDB addresses might be less of a concern for a high-frequency counter application. HBase also offers really high write and update throughput. So if you're going to be doing a lot of writes, HBase might be a better solution than DynamoDB from a performance standpoint. And if you're more concerned with integration with Hadoop services as opposed to AWS services, HBase offers that for you as well. So at the end of the day, sometimes it comes down to what's the ecosystem you're trying to integrate with. If it's really AWS, then DynamoDB is a good choice for your NoSQL database. However, if you're looking to integrate with Hadoop itself, HBase offers more in that department. As with other systems that are on Amazon EMR, they offer some AWS integration points to sort of make it worth your while to use EMR instead of just a straight-up Hadoop cluster from Cloudera or something like that. So like everything else, you're not limited to storing data or reading data from HDFS with HBase on EMR. Through EMRFS, you can actually store files and metadata on Amazon S3 instead. You can also back up data from an HBase database to S3 very easily on EMR. So these are both ways in which AWS has integrated HBase more closely with EMR and AWS services for you. Presto is another technology that comes pre-installed on Amazon EMR, and it's something you might see in the exam. What Presto does is connect to many different big data databases and data stores at once, and allows you to issue SQL-style queries across all of those databases together. So basically, you can write a SQL join command that combines data from different databases stored in different technologies that live on your cluster. It's a way of unifying all of your data and issuing queries across disparate data sources that are stored across your cluster. Now, the key words with Presto are that it offers interactive queries at petabyte scale. So if you see a question that talks about petabyte scale and doing interactive queries across a wide variety of data sources, they're probably talking about Presto. Presto is great because it has a very familiar SQL syntax. There's no new language to learn there, really. And it's optimized for OLAP applications, doing analytical queries and data warehousing kinds of queries across your massive data sets that are spread out across your entire EMR cluster. What's interesting is that Presto was originally developed by Facebook and is still partially maintained by them, so it is open source, but it has its roots in Facebook, and obviously they have big data to deal with as well. Also interesting is that this is what Amazon Athena uses under the hood. So Athena is really just a serverless version of Presto, and with a nice little skin on top of it. Presto also exposes JDBC, command line, and Tableau interfaces, so you can use it as sort of a window into all the data stored on your cluster, and you can expose that to external analytics and visualization tools using these external interfaces. So great way to expose the data on your cluster, even if it's stored in many different places in different formats. Some of those connectors include HDFS, S3, Cassandra, which is another NoSQL kind of database, MongoDB, HBase, straight-up SQL databases, whatever they might be. Redshift is also there, and Teradata. So again, a very wide variety of data sources that you can tie together using Presto. And they can be both relational and non-relational databases. Like, it doesn't care. It can treat them all as a SQL interface, which is really interesting. Presto is even faster than Hive in many cases, and Hive is pretty darn fast, so that's pretty impressive, right? And with Amazon EMR, you can launch a Presto cluster in just minutes. You don't have to do node provisioning or cluster setup or Presto configuration or cluster tuning. So it's very fast and easy to get Presto up and running with EMR. Now in Presto, all of the processing is done in memory and pipelined across the network in between stages. This avoids any unnecessary I/O overhead, and that's why it's so fast. However, even as fast as it is, it's still not an appropriate choice for OLTP or batch processing. Presto is just an efficient interactive query tool for doing OLAP-style queries, trying to extract meaning from massive data sets that might be stored in different databases entirely across your ecosystem. Apache Zeppelin is something else you might see in the exam, and it also comes pre-installed on EMR. Now, if you've ever seen an IPython notebook, that's basically what Apache Zeppelin is. It's a hosted notebook on your cluster that allows you to interactively run Python scripts and code against your data that's stored on your cluster. And it can interleave with nicely formatted notes and allows you to share these notebooks with other people that are using your cluster. So the nice thing is that instead of running a little IPython notebook on your desktop, it's actually running on your cluster. That means you can kick off processes on your cluster and run various data analytics tasks across the entire cluster right from an interactive notebook environment. If you don't know what an IPython notebook is, basically it's a web browser interface that allows you to write little blocks of Python code and see the results interactively. And it also lets you sort of intersperse little comments and notes and pictures if you want to, so that other people can understand what you're doing when they look at your code in the notebook. Zeppelin integrates with Apache Spark, JDBC, HBase, Elasticsearch, and more, so there's a lot of different things you can kick off from a Zeppelin notebook. Personally, I've usually used it in the context of Apache Spark, and the power of Zeppelin is that it allows you to run Spark code interactively, just like you could within a Spark shell. So you can write a notebook on Zeppelin where you just type in some interactive Python code, and it will go off and do that for you across your cluster. This is useful for really speeding up your development cycle because it's a good way of iteratively trying new things with Apache Spark and seeing the results right away. It allows easy experimentation and exploration of your big data. What's really cool is that it makes it easy to visualize your results in charts and graphs. So normally when you're writing Spark code, you're not going to be able to actually produce pretty charts and graphs to visualize the results. But because Zeppelin integrates with external chart libraries and visualization libraries, it makes it easy not only just to kick off a job to Apache Spark, but also to visualize that data in a meaningful way that might, provide new insights from a business standpoint. It also allows you to issue SQL queries directly against your data using Spark SQL. So it makes it very easy to just type in a SQL query and kick that off against your entire data set on the cluster using Apache Spark. So at the end of the day, Zeppelin helps to make Spark feel less like a programming environment and more like a data science tool. So in the world of data science, people very often use IPython notebooks, and this is a very similar format for getting the same sort of capability, except using the entire power of your cluster in Apache Spark to get back those results. So think of Zeppelin as a way of scaling up an IPython notebook to an entire cluster and handling big data instead of just data that resides on a single computer. Interestingly, Amazon also offers something similar called the EMR notebook. And this is a similar concept to Apache Zeppelin, but with more AWS integration. And here's a picture of what that might look like, guys. So, if you're having trouble visualizing what a notebook looks like, this is what a notebook looks like. Basically little blocks of code that you can type in through a web browser that you can just hit Shift-Enter and it will go and execute it for you and give you back the results. Now, the interesting things about EMR Notebook are, first of all, they're backed up automatically to S3, so you're never going to lose them if your cluster shuts down. But actually, EMR notebooks exist outside of the cluster itself. So you can actually make an EMR notebook that provisions clusters and shuts them down directly from the notebook. So imagine, if you will, a EMR notebook that says, go spin up this Spark cluster, do all this data crunching on it, give me the results back, visualize it, store it back in S3 someplace, and then shut that cluster down. So it's a way of very simply writing these scripts that can not only analyze data on an existing cluster, but also spin up clusters on demand to do what you need. So that's kind of an interesting capability. They are hosted inside of VPC for security purposes, and you can only get at them through the AWS console. It has some other great features as well. They are packaged with some popular open source graphical libraries from the Anaconda repository, and that helps you to prototype code and visualize results and perform exploratory analysis with Spark data frames. They can be attached to an existing cluster, or you can provision new clusters directly from the notebook. Like I said, that's a very important capability. And it allows multiple users from your organization to create their own notebooks, attach them to shared multi-tenant EMR clusters, and just start experimenting with Apache Spark. This is provided at no additional charge to Amazon EMR customers, so that's really nice. A really nice little value add to the Hadoop cluster running on EMR is the EMR notebook. There are several other technologies that are associated with EMR that you need to at least know what they are. You're not going to need a whole lot of depth on these, so I'm just going to spend one slide on each one. The important things here are what each technology does and how it integrates with AWS. Those are the key points. Let's start with Hue. HUE stands for Hadoop User Experience. And basically, this is the front end for your entire cluster. It's like the manager for your entire cluster. So think of it as sort of like the front end interface to managing your entire cluster, spinning up services, getting operational insights into what's going on, things like that. It can integrate with IAM to make sure that your HUE users can inherit IAM roles in terms of what they can access within HUE. And they've also extended HUE to actually allow you to browse and move data between HDFS or EMRFS and S3. So that's kind of how they've extended HUE for EMR. But the main thing you need to remember is that HUE is basically the front-end console, the management console for your entire EMR cluster. Okay, so you might run into questions on the exam that are like, what's the most appropriate tool for this problem? Remember, HUE is just a management tool. It's the front-end dashboard for your entire cluster, if you will. Splunk similarly also offers operational insight into your cluster as a whole. It just sits there collecting and gathering index data all the time about the actual performance of your cluster and what it's doing. And in addition to deploying it on EMR, you can just spin up your own Splunk cluster separately. Amazon offers public AMIs containing Splunk Enterprise on top of a 64-bit Linux Amazon OS that you can just sit there and have it monitor your EMR cluster separately. So again, the important thing here is that Splunk is basically an operational tool. It's used to visualize your EMR and S3 data using your cluster. You're only going to really see Splunk in the context of sort of a list of various technologies that might fit a certain problem, and usually it's just there to misdirect you. But if you know what Splunk does, that will help you understand those questions. It's just an operational tool. So Flume is a little bit more interesting. It's just another way of streaming data into your cluster, kind of like Kinesis or Kafka might do. So it's a distributed, reliable, and available service that allows you to efficiently collect, aggregate, and move large amounts of log data in particular. So Flume refers to like a log flume from the logging days. It's really purpose-built for log data coming in from a big fleet of web servers, for example. Basically, a web server would act as an external source that provides events to a Flume source. That event is then stored in one or more channels. And a channel acts as a passive store that keeps the event until it is consumed by a Flume sink. The Flume sink then removes the event from the channel and puts it into an external repository like HDFS on your EMR cluster. So an example of a sink would be an HDFS sink that writes events into HDFS. It supports creating text and sequence files and supports compression in both file types as well. You can also have a Hive sink, and that would stream events containing delimited text or JSON data directly into a Hive table, or partition events are written using Hive transactions. So it's just a way of streaming data from external log sources directly into HDFS or Hive or HBase or what have you. The underlying architecture isn't that important. You just need to understand what Flume is for. It's a way of streaming log data into a cluster. So in that context, you might see it as an alternative technology for handling streaming applications on an EMR cluster. Let's also talk about MXNet. We haven't really talked about deep learning yet, but MXNet is an alternative to TensorFlow, and it is a library for building and accelerating neural networks. It is included on EMR, and it seems to be kind of the preferred way of doing deep learning on EMR. So all you need to really know for the purpose of the exam, they're not going to ask you to design a neural network. Don't worry about that. But you do need to know that MXNet is a framework that is used to build deep learning applications. Okay, so MXNet is basically a library that makes it easy to write deep learning that is distributed across an entire EMR cluster. That's it. That's all you need to know. Another tool you might see on the exam is S3 Dist CP. And what this is a tool for copying massive amounts of data either from S3 into HDFS or from HDFS into S3. And because it uses MapReduce, it's able to split up the copying of your objects across all the machines in your cluster. So it's a very efficient way of copying a lot of numbers of objects in parallel using your entire cluster to do it all at once. So again, it uses MapReduce to copy stuff between S3 and HDFS in a distributed manner, and it can work across S3 buckets, and it can even work across different AWS accounts. So just know what it is and what it's for. That's what's important here. And there's a bunch of other external tools that you might see running on a Hadoop cluster in general. Not all of these come pre-installed, but many of them do. Again, you just need to know what they are. There's no need to go into a lot of depth as to how they operate. You just need to know what they're for the purpose of the exam. A lot of these you'll just see in the context of they're going to throw this out there to misdirect you, but once in a while, they'll expect you to actually know what it is. For example, Ganglia is actually a monitoring tool that comes pre-installed on EMR. It's just a way of monitoring the status of your cluster. You probably want to use CloudWatch for that in most cases, but Ganglia comes as part of EMR as well. Mahout is actually a machine learning library. So if you see a question that's asking about ways of doing machine learning on an EMR cluster, that might be a legitimate way of doing it. Obviously, deep learning and using something like MXNet or TensorFlow is also another way of doing it, but Mahout is also a way to do it as well. It's also in the same league as like Spark's MLlib that we talked about earlier. So there's a lot of ways to do machine learning across a cluster. Mahout is yet another one of them. And if you want yet another NoSQL database, in addition to HBase and DynamoDB, we have Accumulo. The thing about Accumulo is that it's designed with security primarily in mind, but it is fundamentally just another NoSQL database. Scoop is interesting. That might come up. That is basically a relational database connector, and it's used primarily for importing data from external databases into your cluster in a very scalable manner. So kind of like S3 DistCP parallelizes the copying of data between S3 in your cluster, Scoop can parallelize the copying of data from an external relational database into your cluster as well. So Scoop's raison d'etre is to parallelize the importing and exporting of data between external relational databases and your cluster. That might be important to know. There's also something called hCatalog, and what that is table and storage management for your Hive metastore. So it's kind of a meta layer on top of the meta store, if you will. It's a storage and table management for Hive metastore, just like it says. That's all it is. So if you see the term hCatalog, that's related to Hive metastores and in turn related to Hive. Also, there's a thing called the Kinesis connector. This is just a little library that lets you directly access Kinesis streams from any script that you might be writing. So if you do need to have a situation where you're writing your own custom code on an EC2 node or something, you might use Kinesis connector to access the data in that stream from a script that you're writing. There's something called Tachyon that might get mentioned. All Tachyon is an accelerator for Apache Spark. So even though Spark is pretty darn fast in its own right, there's an add-on called Tachyon that will make it even faster. And if you're looking for yet another relational database, there's something called Derby. That is an open source relational database that's implemented entirely in Java. So the thing that makes that database different is that it's entirely done in Java and uses objects in Java primarily. Finally, there's a Ranger, Apache Ranger, that is a data security manager for Hadoop, just another third-party tool. None of these are specific to EMR. They're all general-purpose tools that exist in the Hadoop ecosystem. There's nothing really special about them in the context of a EMR cluster. They're just things that you might install on any Hadoop cluster in general. But this is an exam about big data, and once in a while they'll expect you to understand things that are not necessarily within the AWS ecosystem, but within the larger Hadoop big data ecosystem as well. And in addition, you can install whatever software you want on your EMR cluster. At the end of the day, it's just a cluster of EC2 hosts, and you can install any external third-party systems you want on there. No one's going to stop you. So, if you have your own custom software or some other third-party package that you want to run in your cluster, have at it. Why not? You can do whatever you want. You have complete access to this cluster. You can install whatever you want on it to do whatever you want. So keep that in mind too. You're not limited to the tools that come pre-installed on EMR. So let's summarize the world of security in EMR. So let's talk about IAM policies to start. Obviously, EMR integrates with IAM for permissions, and you can use IAM policies to grant or deny permissions and determine what actions a user can perform with Amazon EMR and with other AWS resources. Now, you can also combine IAM policies with tagging to control access on a cluster-by-cluster basis. So you can tag your clusters and organize your policies that way. We have Kerberos available to us as well that provides strong authentication through secret key cryptography. It's a network authentication protocol that ensures that your passwords and other credentials are not sent over the network in an unencrypted format. So any modern version of EMR will support Kerberos, and you can find more details at the AWS documentation. But that's probably all you need to know. SSH, of course, is used for secure connections to the command prompt on the individual instances inside your EMR cluster. And you can also use it for tunneling to web interfaces. So some of the applications that are running on your cluster will have web-based UIs for either configuring them or monitoring them. And you can use an SSH tunnel to view those securely from your desktop. Kerberos or Amazon EC2 key pairs can be used for client authentication with SSH. And then we have IAM roles. And that can be used in a few ways. So one is IAM roles for EMRFS requests to Amazon S3. So you can get some fine control over the permissions there in that boundary between EMR and S3. You can control whether cluster users can access files from within Amazon EMR based on user, group, or the location of EMRFS data within Amazon S3. So that allows you to lock down what your cluster can access to what buckets and locations within S3 should have access to that cluster. Also note that the Amazon EMR service role, instance profile, and service linked role control how Amazon EMR is able to access other AWS services. Each cluster in Amazon EMR must have a service role and a role for the Amazon EC2 instance profile. IAM policies that are attached to these roles provide permissions for the cluster to interoperate with other AWS services on behalf of a user. If you're going to be using automatic scaling, you also need to make sure that an auto scaling role is in place. And if the service for Amazon EMR has lost the ability to clean up Amazon EC2 resources, you want to make sure it has the appropriate service linked role as well. Another important tool in your EMR security toolbox is the setting for block public access. So if you want an easy way to prevent public access to your data stored on your EMR cluster, you can simply enable the block public access option at the account level before you create your cluster. It's just that easy. So if you want to make sure nobody can get at the data that's actually stored on the cluster itself, all you have to do is say block public access and do that before you create the cluster, and you're done. It's just that simple. You're still responsible for securing any underlying data, of course, that EMR is accessing. So, if you're accessing data that's stored in S3, you're going to have to secure that data through S3. But for the data stored on the cluster itself, block public access is a great tool. So for 2021, we have some new guidance on choosing instance types for your EMR cluster. Remember, you get to choose what actually powers your cluster for each node type when you launch the cluster. So you need to have a master node, obviously, and what Amazon currently recommends is that if your cluster is less than 50 nodes, go with an M5.X large type for the master node. If you have a really big cluster that's more than 50 nodes, then you want to go with an even larger type than M5X large. But for under 50, M5.X large is what they're recommending. Then we have your core and your task nodes. And generally speaking, an M5.X large is usually good for that as well. So for a typical cluster with less than 50 nodes, you can use that same type for your master, core, and task nodes. However, there are special cases. If your cluster is waiting a lot on external dependencies, like you've written a web crawler or something like that, where you're just sitting around waiting for network traffic all the time, maybe you can get away with something a little bit less expensive, like a T2.medium. If you need more performance, though, you need to go the other direction, you can step up to an M4.X large for your core and task nodes as well. Obviously, if you're doing something that's really computation intensive, and some of the ML applications might fall into that category, you might want to go with a high CPU instance type instead. And if you're doing something that's really memory intensive, like a database or something that's doing a lot of memory caching, a high memory instance might be an appropriate choice instead too. And of course, there's also network intensive or CPU intensive applications out there too, such as natural language processing and again, machine learning. Maybe cluster computer instances would be the right choice for those types of applications. And remember, for task nodes, a spot instance is often a good choice. You can only use those on core and master nodes if you're testing things or extremely cost sensitive. You're always risking partial data loss if you're using a spot instance on a core or a master node. They're usually only a decent choice for task nodes where they're only being used for processing and not for data storage. For our next hands-on activity, we're going to build a product recommendation system for Cadabra.com. And the good news is that we've already built out most of this system way back in exercise 1. So we already have an EC2 instance that is populating server logs that get consumed by a Kinesis Data Firehose, which in turn dumps that data into an Amazon S3 bucket. And this has already been set up, and you might recall that we already put 500,000 rows of data into S3 to sort of make a little data lake, if you will, of order data that we can then play with. So all we have to do now is spin up an Amazon EMR cluster and run Apache Spark using MLlib to actually generate a recommendations model based on that order data in S3. So let's dive in and make that happen. Back to the management console in AWS, we're going to select EMR. Just type it in here if you don't see it in your list. And create cluster. Give it a name like Cadabra Rex or something. Default logging is fine. We're going to use the latest DMR release, and we're going to select Spark for the applications here because we are fundamentally building a Spark application using MLlib to create these recommendations. You can see we also have options here for something optimized for Presto, HBase, or just straight up Hadoop. Spark is on top of Hadoop, however, so we are still sitting on top of an HDFS file system here, and we have the Zeppelin notebook here if we want to actually have an interactive notebook on top of Spark that we could play with. Hardware configuration, you have to make sure you select an instance type that is both appropriate to your application and available in the availability zone that you're launching within. And sometimes you have to kind of figure that out the hard way. Generally speaking, though, the most recent instance type will be available in most availability zones. So let's go ahead and change that M3 to M5 just to be safe. Now, I want to stress again here that we are incurring real charges here. An EMR cluster does not fall within the free usage tier. So if you are squeamish about incurring any charges as part of this course, do not follow along here, because once we create this cluster, you will start getting billed. It's not much. We're just going to be running it for, about less than an hour. But, if you don't want to spend any money, just watch. We will stick with 3 instances because we do want to run on a real cluster here and not just a single machine. We will select an EC2 key pair. We can just reuse the one that we made for our EC2 instance before that contains our log data, and hit Create Cluster. It will take a few minutes for this cluster to spin up, so we're just going to have to wait for it until starting says something a little bit more encouraging about being able to actually connect to it and actually work with it. So we'll pause here and come back when that's ready. All right, it took several minutes, but it looks like our cluster is finally up and running and waiting to go here. A quick word about the instance types here a little bit more. So we did successfully provision a m5.xlarge for our master node and 2 core slave nodes there, also m5.xlarges. Now, you want to generally think a little bit more deeply about what instance type makes sense for your application. In this case, we're using Apache Spark doing machine learning, and machine learning tends to be a very CPU-heavy operation. So maybe a C5 would have been a better choice there. It just turns out that that instance type isn't actually available in my availability zone. So sometimes you just have to go with what's available, and a general purpose m5.xlarge is usually good enough for most applications. Now, if you were doing something with deep learning, for example, that would be more of a GPU-intensive operation. So if you're building big neural networks using TensorFlow or something on this cluster, you'd want to use a GPU-optimized cluster instead. But we're going to stick with m5.xlarge. What we're doing isn't actually all that taxing, so it doesn't really matter that much for our little example here. So before we can actually connect to our master node and run our Spark script from it, first we need to open up that node to SSH from our PC here at home. So by default, that's not set up for you, and they don't really tell you about that. Go down to the security groups for master and click on that. And we're going to select the Elastic MapReduce-master group name here. And if you go to inbound, you'll see that port 22 is not in here. So there's really no way to connect to this from a terminal right now. So let's fix that. Hit edit. Scroll down, we'll add a rule. Custom TCP rule, TCP port 22. And let's set this to my IP. Of course, that'll be different for you. Hit save. And now we should have some hope of actually connecting to that master node. So go back and click on master public DNS here. If you click on SSH, it will give you the instructions you need from PuTTY. We'll just going to use that for our connection host there. Copy that, fire up PuTTY. Put that in the host name, and as before, go to SSH, click on auth, and select our key file that we use when creating this cluster. The host key is fine. You can click OK on that, and we're logged in. So cool. We are logged into the master node of our Hadoop cluster here on Amazon Elastic MapReduce, and it's all set up for Apache Spark for us already. Pretty easy. All right, so before we start writing our own machine learning algorithms for recommender systems from scratch, that's a whole other course. So let's just start by using one of the samples that actually comes with Spark that produces recommendations using an algorithm called ALS, alternating least squares. And that lives under the samples directory of Spark itself. Let's make a copy of that to our home directory so we can start from that and just mess around with it. So we're going to type in cp, the copy, /user/lib /spark/examples /source/main/python/ml. Now we're getting the machine learning stuff. It's getting interesting. and als underscore example.py / to copy it right here into our home directory. And there it is. Let's take a look at it. Nano als example.py. And we can just kind of scroll through here, see what's going on. Okay, so you can see we're importing PySpark. So this is a Python script that is a Spark driver script. It kicks off a Spark session, calls it als example, reads in data here from something called sample movie lens ratings.txt. So by default, it's using some movie ratings data. That's part of a public data set called movie lens. And it's looking for it in the data mllib als sample movie lens ratings.txt path. Now that is not a local file path. Notice that there's no file protocol in front of that. There's no S3 in front of it either. So it's actually going to be looking in the HDFS file system on this cluster. Remember, we're running Spark on EMR on top of a Hadoop cluster here, and it does have an HDFS file system that's shared amongst all the different nodes in this cluster. So very important that we're reading from a location that every node in the cluster can read from. If that was reading from a local directory, all the other nodes in the cluster wouldn't be able to get at that, right? So it's implicit that this data lives in the HDFS file system, not on your local file system. So we're going to have to make sure that data is there before we do anything else. Remember that. From there, we don't really want to get into the details of Spark so much. That's not going to be covered on the exam, but at a very high level, it's reading every line of that movie ratings data. It's mapping it out to actually split that up based on its individual fields. It looks like it's delimited by double colon characters. It then creates rows into an RDD by splitting out the user ID, movie ID, rating, and timestamp for each movie rating. Creates a data frame from that, splits that into a training and test set, and then it creates this ALS recommendation model, which is just part of MLlib. It does all the heavy lifting for you, using some parameters that make sense for it. And after that, we just train the model based on the training data that we extracted from that ratings RDD, and then we can make predictions from that to actually try to see if we can actually predict the ratings of a given movie that the model doesn't know about yet. And we measure the root mean square error as a measure of measuring the quality of those predictions. And just to see some actual results, we generate both the top 10 movie recommendations for each user and, flipping it on its head, the user recommendations for each movie. So we can actually go in both directions here. Not only can we recommend movies for users, we can recommend users for movies, which is kind of an interesting take. In our case, for order data, we're going to be recommending orders like items, actual physical products, and not movies. But otherwise, it's the same thing. So with that high-level understanding, let's exit out of this, Control X. And like we said, we need to give it some data to play with. I just want to make sure that this script runs before we start messing with it. So we're going to actually copy that sample data into Hadoop's HDFS file system. Let's do the following. Hadoop fs/makedir, we need to give this thing a home to go into, -p/user/hadoop/data/mllib/als. So that created that directory in the HDFS file system that's shared across this cluster. Now let's copy that data into it. Hadoop fs-copy from local /user/lib/spark/data/data/mllib/als/sample movie lens ratings.txt. So this is copying from the local path and putting it into HDFS under the same place, more or less, /user with an E /hadoop/data/mllib/als/sample _movie lens _ratings.txt. Double check everything here. One small typo will mess everything up. So let's see. Yep, looks good to me. And that has copied that sample data into the HDFS file system where the entire cluster can get at it. Let's see if it works. So to actually run a Spark script from the master node, you need to use the spark-submit command, followed by the script itself, alsexample.py. And let's see what happens. That should, in theory, distribute that script across the entire cluster of 3 machines, and that entire cluster will just start chewing on the data and building that recommendation model and see what happens. Now, it's a little bit annoying here. There's all these info messages coming up that are kind of like hiding the actual things that we care about. So far so good. I'm not seeing any errors. Things seem to be happening here. It looks like Yarn is actually scheduling some work. That's a good sign. It's doing stuff, doing more stuff. And, if there's anything like in terms of useful results being produced, I wouldn't know because there's so many of these info messages going by. Like it's probably buried in there somewhere, right? So let's just let this finish. The first thing we're going to have to do is fix that info message issue. All right, it finished. I have no idea what the output was, though, because it's lost in all these info messages. So let's go get rid of those info messages, shall we? Sudo nano als example.py. And we're going to add a little line in here. So right after the Spark session is created, right there, let's add a new line and say spark.sparkContext, the capital C, set log level. Again, pay attention to caps there. Error, just like that. So this means that I only want to see log messages that are at the error level. Everything else, please suppress for me. Now this is only going to take effect after the Spark session has actually been created. So we're still going to get a bunch of info messages until this script actually starts running. But once it starts doing interesting work, those messages will be suppressed. So we should be able to see our final output more easily. Control O to write that out, enter, and Control X. And let's try running that again. Spark-submit alsexample.py and give that another go. So again, we're still seeing info messages while it's spinning things up, but once it actually starts running the driver script, those should go away. Oh, cool, a result. So it actually printed out our root mean square error there. This is not a machine learning class, so I'm not going to get into what that means. It's just a metric of how well it does. And look, results! Awesome. So we can finally see them with all those info messages out of the way. And you can see there, for example, user ID 26 had movie ID 90 recommended with a predicted rating of 6, which doesn't make sense because it goes from 1 to 5, but it's really, really confident about movie ID 90, whatever that is for user ID 26. And flipping it on its head, we also have our movie ID with user recommendations and predicted ratings from them as well. Cool, so we have something that works here. We can build upon that now to actually work with our data set instead of this fabricated sample movie ratings data set. So to do that, to make life easier for you, I have actually given you that code in the course materials. But first, we need to make sure that our S3 bucket that contains the order data that we want to use instead is accessible to this script. So let's head back to the AWS console here, go back to S3, and go into the bucket that we created originally back in exercise 1. Now for you, this will be different depending on when you actually ran the script. It buckets this up based on when you actually ran it and generated those logs from. So for me, that's going to be here. Just go to the very first date that you see and the very first hour that you see under that, because that's going back to exercise 1 where we actually output 500,000 rows of data. So that's a pretty meaningful data set there. All right, let's go back up one level here and actually select that final folder here and make that public. Normally this is a horrible thing to do, of course, but this isn't sensitive data. It's a public data set, so I'm not too worried about it. All right, so now that data should be accessible to our Spark script. Let's go back to our cluster here. And if you go to the course materials, we can see the changes that we want to make. Just go into the product recommendations folder here and open up als-modifications.txt. These are the snippets of code that we want to replace. So we're changing the source of the data here to S3 where we actually stored that data. So the first thing you need to do is change that to where your S3 bucket is. Remember, you have a unique name, so you're going to have to change that to match your bucket name. It should be still up here in the URL for S3 where you were messing around with that. So let's make sure that matches up with this. So instead of 211.16, I'm going to change that to 225.20. Again, make sure this matches the folder within the bucket that you created for the 500,000 rows of order information that you created back in exercise 1. It will be different from what you see here. From there, we need to change a few more things. First of all, the delimiter is not double colons, it's just a comma for us. We're also going to do a little bit of data cleanup here. So it turns out that there's a lot of junk in this data set. And if we don't filter that out, we're going to get some weird results. So what these two lines here are doing are just making sure that we're only taking in order IDs and customer IDs that actually have digits in them. There's a lot of special cases in the data that deal with giving people free shipping or postage or dealing with discounts and commissions and bank charges. Those don't reflect people actually buying things. They don't reflect an actual indication of interest. So we need to clean that data and filter that data out ahead of time. That's what's going on here. It's a good reminder that in any machine learning, data cleaning is a big part of what you're doing. Garbage in, garbage out, guys, right? So you want to make sure that the behavior data that you're training your systems on really is behavior data from real people for real items. And we had to do some work to make sure that happens. After that, we just constructed our rows differently. We made sure that we extracted our customer IDs, item IDs, and ratings. Thusly, since these aren't really ratings, we're treating them as implicit ratings. We're saying anytime that somebody buys something, implicitly we're saying that person liked that thing. And it corresponds to a rating of 1.0, as opposed to a rating of nothing if they didn't buy something. So let's go ahead and copy this into our clipboard, back to our EC2 master node here on the EMR cluster. Let's edit our driver script. All right. So let's get this code side by side so I can see where it has to go. So basically we're starting with this bit of code here and replacing everything down to where it constructs ratings RDD, right? So basically those three lines are going to get replaced. So Control K, Control K, Control K, Control K. And I'm going to right click to paste that in. All right, looks good. So that should work. Let's hit Control O to write that out, enter Control X and kick that off again and see what happens. So once again, we'll do Spark submit alsexample.py, kick that off and let it do its thing. Again, it is going to distribute this across our entire cluster of 3 nodes and process those 500,000 lines of order information to construct a recommendation model and actually make some predictions for some real users based on that model. Give that a minute to finish. All right, I actually got an error here, so apparently I missed something. Another learning opportunity here. The error message, fortunately, is pretty straightforward. It's complaining that we're looking for something called user ID, and that doesn't exist in our data, so I must have missed something. Let's go back and edit that script again. Again, debugging is part of the process here, guys, so it's just what you do. Well, there's where user ID shows up, and it makes sense now. I basically forgot to change this model to specify what the actual column names are that I'm using for user identifiers and item identifiers. So for me, it's not user ID, it's customer ID. So let's go ahead and change that to customer instead of user. And we're not dealing with movie IDs either. We're dealing with item IDs. So let's go ahead and save that again. Control O, enter, Control X, and try it again. Spark submit alsexample.py and see what happens this time. All right, looks like we're getting some results here. So our script is working. Our RMC error was pretty low there. That's encouraging. And here are some actual results. Cool. All right, we got a few sample results here for some sample customers. So customer ID 13098 apparently we think would really like item ID 79342, whatever the heck that is. So this isn't very intuitive, like what does item ID 21899 really mean? And apparently user ID 15299 would really like it. We can look that up if you're curious. So just open up another session here to our actual EC2 node that contains the source log data. And if we go into var-log/cadabra, that's where our original logs exist. We can actually search there to see what that ID means. For example, grep, what is it? 21899 star.log, and you can see that 21899 actually is a garage key fob. So apparently the person in the data set that would most love a garage key fob is user ID 15299 according to our recommender algorithm here. So some real results here, guys. We actually built a real recommender system using Apache Spark on a real EMR cluster. That's kind of awesome. Let's clean up our mess here. Exit out of that EC2 node, and let's also exit out of the master node for our EMR cluster. And again, this cluster does cost real money, so do not forget to shut this down. Let's go back to our console here. Go back to EMR. Click on our cluster and terminate it. All right, do not forget to do that, guys, or else it will add up fast. These are expensive computers, and there's 3 of them, so don't want to keep those running for too long. All right, so that is terminating, so we've cleaned up our mess. And again, you have successfully created a recommender system using Apache Spark's MLlib on an EMR cluster on top of an S3 data lake that was populated from Amazon Kinesis Firehose. How cool is that? Next, let's do a really quick overview of AWS Data Pipeline. You're not going to need a whole lot of depth on this, but you need to know what it is and how it fits into big data workflows. Basically, Data Pipeline lets you schedule tasks for processing your big data. You're not going to need a lot of depth on it, but you need to know what it does. So let's just look at an example here. Let's imagine that we have log files that are published on EC2 instances, and we need to publish those log files into S3 and later analyze them using EMR, some process running on our EMR cluster, maybe Spark or something. So Data Pipeline can schedule a daily task or whatever frequency you want to copy those log files from EC2 into S3. Again, this is just an example. It can do many different things. And then, maybe on a weekly task basis, launch that data analysis on the data that's been stored up in S3. So if you're familiar with Hadoop, it's kind of like Oozie. It's basically a task scheduling framework where you can run different operations that depend on each other on different schedules. Basically, it's a web service that helps you reliably process and move data between different AWS compute and storage services at specified intervals. In this case, we're copying data from EC2 instances to S3 on a daily basis, and then on a weekly basis, we might analyze that data that's accumulated using an EMR cluster. That's just one example of how Data Pipeline might be used. Very simple concept. Let's go into a little bit more depth about Data Pipeline and what it can do. So destinations that can be used by Data Pipeline include S3, like we talked about. It can also work with RDS, the Relational Database Service, DynamoDB, Redshift, and EMR. So all of those things can be controlled by Data Pipeline. It manages all the task dependencies for you, and it will automatically retry things as necessary and notify you when something fails. It can also have pipelines that work across regions. And it also has features for precondition checks, so you can make sure that the data that you're trying to process is really ready before you try to do something with it. Here are some examples of precondition checks that you might be able to do with Data Pipeline. One is called DynamoDB Data Exists, so that can check for the existence of data inside a DynamoDB table before you try to move it or process it somewhere else. There's also a DynamoDB Table Exists that can check for the existence of an entire table. For S3, we have S3 key exists and S3 prefix exists, which can both be used to test for the existence of either a specific path in S3 or a specific prefix, sort of a path that exists within S3 itself. There's also the shell command precondition, and this runs an arbitrary script of your own on your resources and checks that the script succeeds. So with that precondition check, you can pretty much do anything you want. You can write a script that checks for whatever you want to, and your data pipeline won't kick off until that precondition has been satisfied. You can also use on-premises data, which is kind of interesting for your data sources. You can data pipeline data sources which are residing on on-premise machines. The way that works is you install a task runner on your on-premise machines, kind of like the Kinesis agent that we installed for Kinesis. And then AWS Data Pipeline will communicate with the task runner and manage the flow of data and schedules accordingly. Now, in order to ensure that your pipeline activities are highly available, you can optionally assign multiple task runners to pull for a given job as well. So, very highly reliable system, a lot of different ways you can use it, but at the end of the day, it's used for chaining things together on a schedule and doing so in a reliable manner. There are several different activities that a data pipeline can do, and an activity is an action that AWS Data Pipeline initiates on your behalf as part of a pipeline. Different types of activities include EMR, which allows you to run arbitrary Amazon EMR jobs. Remember, it's possible to spin up an EMR instance and run a sequence of steps automatically and then automatically terminate the cluster when it's done. So that's the sort of thing that a data pipeline event, or activity rather, might kick off. There's also a Hive activity, which allows you to execute Hive queries on a schedule. There's also a copy activity that can be used to copy data between Amazon S3 and JDBC data sources, or to run a SQL query and copy its output into Amazon S3. You can also have SQL query activities, which do exactly what they sound like. They run SQL queries. And there are also command line scripts that can be triggered by activities. That activity allows you to run arbitrary Linux shell commands or programs as part of your data pipeline. You can specify this as a custom activity, or it will be automatically added if you're using any of the templates specified by AWS during the pipeline creation. So a lot of times it can automate the creation of these things for you. Now, by default, an activity will retry 3 times before entering a hard failure state. You can increase the number of automatic retries up to 10 if you want to. After an activity exhausts its attempts, it will trigger any configured on failure alarm, and it will not try to run again unless we manually issue a rerun command via the command line interface or the API or the console button. So that's data pipeline in a nutshell. Very simple concept. All you need to remember is what it does, how it's used, and the systems that it can integrate with. Let's do a high-level overview of AWS step functions. Very similar to data pipelines in concept here. Basically, its purpose in life is to let you design workflows throughout AWS. So as you're building a system to analyze your data and pre-process that data, step functions might be what connects all those steps together to create a larger system. It also lets you visualize these workflows very easily, as we'll see shortly. It generates these nice little graphs to show you the order that things actually execute within. And it also has an advanced error handling mechanism and a retry mechanism that lives outside of the code that you're actually running within your AWS step function. So that's a good utility for being able to manage portions of your workflow that don't work. You don't have to rely on the code of each step actually being able to monitor itself. AWS step functions can take a look at it from the outside and deal with errors when things don't do what they're supposed to do. It also maintains an audit history of all the workflows that have run, so you can go back and see what happened historically if you need to troubleshoot something. It allows you to wait an arbitrary amount of time between steps, so if you just want to place some time in between these steps and sync up with some business workflow that you have, you can do that. And the maximum execution time of a given state machine, that's a given workflow, is 1 year. So you can actually define a workflow that spans an entire year if you want to. Can't imagine a situation where you need to do that, but if you need to, it can handle very long-lived processes and workflows. The syntax of how it all works really is not important. They're defined using the JSON-based Amazon States language, or ASL. The exam will not expect you to be able to parse or write this kind of code or know ASL. You just need to know what it does. So as long as you know what step functions are for and some examples of what you might use it for, that's what's important for the exam. So we're going to go through a few examples of how you might use step functions in the real world. Here's an example of using it to train a machine learning model. So you can see that when we start, we generate the data set. In this example, it's doing that by kicking off a Lambda function. It then trains the model using SageMaker's XGBoost algorithm. And when it's done, it saves that trained model from SageMaker and applies a batch transform to that model from some data set that we had. At that point, it's done. So you can see here, we've automated the entire process of generating our data, training a machine learning model using that data, saving that trained model, and then applying data to that trained model, all in one set of steps here that are managed through step functions. We can also use it to tune a machine learning model. So in this example, we're generating a training data set, and then we're going to kick off a hyperparameter tuning job in SageMaker that just tries different parameters on the machine learning model to figure out what the right set of parameters are for this given data set. When it's done, it extracts that model path, and then it saves the tuned model that it settled on. We extract the model name of the tuned model, and then use that to apply a transformation of a bunch of data in a batch format to that tuned model automatically. So again, just an example of what you might use step functions for. It's not important for the exam to understand how machine learning works, but it is important to know that step functions can automate the process of generating your data set and feeding it into a machine learning model. You can also use it, for example, to manage a batch job. So in this example, we're submitting a batch job, and then we're just going to use step functions to notify us if it succeeds or fails. Very simple. So step functions don't have to be complicated. They can just be used to monitor a single job and use those features that it has to actually monitor and alert us when something succeeds or fails from a given step. So sometimes step functions just have one step. And that's really all the depth you need for AWS step functions. You just need to know that they manage workflows, and they give you a nice graphical representation of those workflows, and they can monitor whether individual steps succeed or fail and notify you based on what happens there.